instead of just predicting the next token or next multiple tokens, what if after predicting a single next token, we also take entire vocabulary of tokens and rank which token is closest to the next token, which is less closer, less close, less close, less close. So ranking each token in vocabulary, how close it is to the current token, is easier than trying to independently predict every single next token in multi-token prediction. So this can potentially make the LLM learn better, faster, and easier. Predicting the order of upcoming tokens improves language modeling. Multi-token prediction has been proposed as an auxiliary objective to improve next token prediction. This happens in DeepSeek v3, but it just happens during training. It trains to predict 2 more tokens, but during inference it just predicts 1. So the idea here is that LLM will learn to think about even the tokens after when predicting the next token during the training. So it will just learn better for less compute. So let's actually explain this article with Gemini. It's really good, it's really accurate, and it's more understandable. Because it's getting really complex even at this sentence here, so it's gonna be more technical. So let's adapt it for more YouTube and easier to understand way while actually learning the same thing. Large language models like GPT-4 and Llama 3 are trained on a surprisingly simple principle, next token prediction. And predicting multiple tokens ahead lets the model learn deeper understanding of language. However, multi-token prediction has mixed results. A new paper from Mohammed bin Zayed University, I'm not sure how to pronounce this, of artificial intelligence, predicting the order of upcoming tokens improves language modeling, argues that multi-token prediction's problem is that it's too difficult. Predicting the exact word 5 steps ahead is a monumental task, of course. They propose a simpler, more elegant solution: token order prediction. The new idea: predict the order, not the token. The researchers hypothesized that if multi-token prediction is too hard, a relaxed version of the task might be more beneficial. Instead of asking the model to predict the exact featured tokens, they ask it a simpler question. Out of all the possible words in the dictionary, which ones will appear soonest? This is the core of token order prediction, TOP. The model doesn't have to guess the exact word at position t plus 5, it just has to learn that the word appearing at t plus 5 should get a higher proximity score than a word appearing at t plus 10. So t is the current, plus 10 means 10 tokens in advance, which in turn should get a higher score than a word that doesn't appear at all. Example, imagine the input text is "the quick brown fox jumps." The model is at the position right before quick, so the next token is quick, so next token prediction will predict quick. Multi-token should predict quick brown fox jumps. This is very difficult, but token order prediction creates a ranked list for the entire vocabulary. So quick gets the highest score, it's closest. Brown gets second highest, fox gets third highest, etc. And then words that are not in the text in the sequence get very low score. This task forces the model to think ahead, to plan ahead, but in a lot more manageable way. And I think Anthropic showed that these models do plan multiple tokens ahead. And when I was thinking how can we implement LLMs to do hierarchical reasoning, actually just autoregressive LLMs kind of do hierarchical reasoning, because if I want to fly from Berlin to this other city, I'm first thinking, okay, I need to fly, okay, I need to go to airport, I need to buy a ticket. So actually hierarchical reasoning can also be done in a linear autoregressive fashion. You just think about more abstract things first and then break them down. So I'm not sure how would we make LLM think hierarchically in a different way. This just seems like it's already thinking in a hierarchical reasoning kind of way. But that's besides the point of this. I was just explaining that. How TOP works in practice. Model architecture. The main body of the transformer model remains the same. At the very end, the output is fed into two separate heads, simple linear layers that work in parallel. Here, transformer layers, and we have next token prediction head and top head. Next token prediction just predicts the next token, while top head assigns a score for every token in vocabulary based on its proximity to the current token. The loss function. During training, the model's performance is measured by two losses that are simply added together. Next token prediction loss and top loss, which is learning to rank loss, that compares the model's predicted ranking of tokens with the true ranking from the text. How is this different than multi-token prediction? I'm not sure, because it still needs to predict. What? How is this different? I'm not sure exactly. Okay. So the difference here is that we are not actually adding more layers to the transformer. We are just adding one additional head, and now these layers inside a transformer, they are connected to both of these heads. So with back propagation, they will learn to predict both the order and the next token. So the computational overhead here is smaller. This is just like maybe small auxiliary loss, but I still feel like this is still next token prediction, like multi-token prediction. You are still predicting multiple tokens, it's just maybe less architecture modifications. And during inference, this top head is completely removed, just like in multi-token prediction in DeepSeek. So this is just for training. This is to make internal representations learned during training much richer and more forward-looking. On the surface, both methods are concerned with future tokens, but the fundamental difference lies in the nature of the question being asked for the model. So in multi-token prediction, the token predictions are independent from each other. So you are, for example, in weather analogy, you are asking the exact temperature Tuesday noon, Wednesday noon, Thursday noon. And it's more difficult than in maybe the analogy would be predict which temperature, which day has higher temperature, which day has lower temperature based on like previous days, next days. So if we have a single token, when predicting multiple tokens ahead, we need to predict every single token independently, while in the ordering ranking prediction, we kind of predict all of them at once. I think it's we have more information, it's easier to predict, to order them, than to try to predict every single token independently. That's my understanding of it. They use .1w. I recommend using MuP on n.1w. So they're gonna add multiple experiments to this paper, comparing with DeepSeek v3 version of MTP. So I recommend you can also do this research if any of you want to figure out what research you want to do. Fine-tuning and evaluating on generative tasks such as summarization and coding. And then self-speculative decoding. They tested it on 340 million, 1.8 billion, 7 billion parameters. They say it outperforms NTP, MTP. The problem is oftentimes, in many papers, they don't fine-tune these old methods to perform at their highest performance. So every paper is claiming that they surpassed something, but just because what often happens is that something wasn't tuned to the maximum performance. But anyways, this is promising direction. Maybe they're gonna show us, maybe they're gonna create a good invention here, and this is gonna be used in large language models. We'll see. Check out other videos and join my Discord, and see you next time. I wanna make these courses for beginners to learn, and I wanna make on my Discord, I wanna make like research projects where we can even post papers, but I'm not sure how to do all of that yet. I'm just trying to figure out, so you can help me and give me your ideas. And so see you next time. Let's check this new paper. The first author sent it in my Discord. It tries to solve the quadratic scaling of the attention. My Discord and the paper URLs below the video. So it's from Carnegie Mellon University. If you work with transformers, you know their power. You also know their kryptonite, the dreaded O(n)² complexity of the self-attention mechanism. While this is manageable for text sequences of few thousand tokens, it becomes a computational nightmare when n scales to hundreds of thousands or even millions, as is common in scientific simulations on large meshes or point clouds, or if we have millions of text tokens. So this idea can be applied to that situation as well. The paper FLARE, Fast Low Rank Attention Routing Engine, introduces a clever and highly effective solution to this problem. Let's break down how it works step by step. The core problem: why standard attention fails at scale. So you see the scores, query times key matrix. We all know this, so I will skip this. But you see it's quadratic scaling. The longer this Q, the longer the K. So for each token has its own Q and K. Sometimes it's a bit grouped, so a bit maybe less of the keys. But anyways, it always has this quadratic scaling. So for 1,000,000 tokens, this matrix would have 1,000,000,000,000 entries. That would be almost infeasible or infeasible to compute and store. To have 1,000,000,000 of those results where each key multiplies each query. Key insight: attention is often low rank. The authors of FLARE, like others before them, build on a key observation. The massive n times n attention matrix is often low rank. In simple terms, this means the complex all-to-all communication pattern can be approximated without every token talking directly to every other token. Instead, the information can be routed through a much smaller, intermediate set of hub tokens. It makes sense. When I'm reading a book, I don't actually need, not every word has some correlation with every other word. Just certain words have correlations with some other certain words or sentences, but it's not that every correlates to every other. Imagine a city of n people. Standard attention: every person calls every other person directly, so n squared phone grid. Low rank idea: everyone routes their calls through a central switchboard with just m operators, where m is much smaller than n. FLARE builds a learnable version of this central switchboard. FLARE introduces a fixed size sequence of m learnable latent tokens. These tokens don't come from the input data, they are model parameters, just like the weights in a linear layer. Let's say our input x has n tokens, example n points on a mesh, and our latent sequence has m tokens, let's say m is 128. So input sequence n tokens can be millions, while latent sequence m is a fixed small number, 128. The entire FLARE mechanism is a two-step dance of routing information from the n tokens to the m tokens and then back again. FLARE replaces the single self-attention step with two sequential cross-attention steps. So instead of single self-attention, we have two sequential cross-attentions. Part A: encoding input to latent. The first step is to compress or summarize the information from the n input tokens into the m latent tokens. First, get keys and values. Just like in standard transformer, we create key and value matrices from our input x. These have the shape nd. So d is like dimension, I guess, of each key and value, while n is just the number of tokens. So this is a matrix, one of them for keys, one of them for values. Use latent queries. Here's the magic. Instead of creating a query matrix from the input, we use our learnable latent sequence as the queries, okay? Instead of creating a query matrix from the input, we use our learnable latent sequence, our m sequence, as the queries. Let's call this Q latent with shape MD. And so now we do the cross attention between the latent queries and the input keys values. So we just do Q latent at keys transposed. And then we just use that result for the multiplication with values. The result Z is our compressed latent representation. We've effectively summarized the entire n token sequence into just m tokens. This operation has a complexity of O of n times m, which is linear in n, which is basically because m is a lot smaller and it's consistent. So I guess the way they calculate these complexities is you can just ignore m in this case because it's very small and constant. Then we have decoding that goes from latent to input size again. Now we need to distribute the summarized information from the m latent tokens back to each of the n original tokens. Swap roles. We cleverly reuse the same components. The original input keys now act as the queries. The latent queries, Q latents, now act as the keys. Now I think they just swap. Now use latent values. The compressed repetition Z we just calculated now serve as the values. So these are the latent values that we calculated. Perform a second cross attention. So here queries, which is in our case the keys, a bit confusing here, but just swap keys and queries and then do this. The final output Y has same shape as the input ND, but each token has now received global information that was routed through the latent bottleneck. The second step also has complexity of O of n times m. Looks like you can just use scale.product_attention from PyTorch because this is very good. If you can just use this, it's very optimized, very fast. So this is a cool paper, it's a cool idea. I'm gonna end the video here. For those of you who want to learn more about this, who want to dive deeper into this or use this in your research, I'm gonna leave the link below. The first author is on my Discord, and on this Discord we do like research, we talk about AI. So I'm gonna leave the link below. Also check other videos on my channel and see you next time. Let's understand different optimizers. So Adam, adaptive momentum estimation. It computes adaptive learning rates for each parameter. It does this by keeping the track of two moving averages. The first moment, the mean of the gradients, like momentum, and second moment, the mean of the squared gradients. So just a bunch of averages. So on a steep slope, the ball picks up speed, moves faster. That's the first momentum. So now, on the gentle slope, it still has this speed, this fast movement. It's gonna slow down a little bit though. And if slope changes directions, the gradient descent, the momentum will still resist the change. This eliminates noise where different situations, different gradients go up in a bit a random direction. So now they're all gonna go in kind of similar together in the same direction, the strongest direction. Then we have adaptive learning rates. So not all parameters in a neural network are equally important or need to be updated at the same rate. Some parameters might have very consistent small gradients. We can be confident in their direction and want to update them more aggressively. Take bigger steps because they're moving in the same direction consistently. So just speed it up. Other parameters might have very noisy, large gradients. We should be more cautious and take smaller steps to avoid overshooting the minimum, especially if they're a bit random, so you don't know where you're going. Now this way, now this way, now that way. This is the idea of adaptive learning rates. So Adam gives every single parameter its own individual learning rate, which it adapts as training goes on. It does this by keeping track of the squared gradients. You can ask AI to explain step by step these formulas, but this is better for one-on-one learning with AI. Otherwise, it will be too boring or difficult to understand if I just explained it. Also, the W in Adam W is for weight decay, a regularization technique used to prevent overfitting by penalizing large model weights. You don't want large numbers in neural networks, they mess things up. But this W is just like a bug fix for Adam. You can check here. So, and Adam W is Adam W with Nester of momentum. So it's a bit confusing to me as well, but instead of calculating momentum at the current spot, it just sees if I was to use this momentum to make another step, where would I land? And calculate momentum from there. And then apply momentum from that future hypothetical step in this original step. This can somehow prevent the optimizer from overshooting minimum and can lead to faster convergence. I'm gonna look more into this maybe in a different video. I don't get it 100% how and why. Then we have Mars, make variance reduction shine. This is made to handle the problem of variance in stochastic gradients. So when you train on a bunch of small batches, they're just gonna be noisy average of the big batch. So if you have one big batch, it's gonna be average of all of the small batches. But in small batches, it's gonna be like a bit of noise everywhere. Mars aims to reduce this random noise. So we have variance reduced, estimate of the true gradient. It keeps track of updates of the previous batches, and so kind of averages it, so it's not so noisy. It also does same as the per parameter update like Adam W, the second momentum. Then cautious is a bit of a modification to momentum-based optimizers like Adam W and Lion. Only apply update if optimizer is confident about the direction. So there is a simple check. Does the direction of the gradient and momentum, the previous gradients, the momentum and the current gradient align? By comparing their signs. If one wants to go in one direction and the other has opposite sign in the other direction, then the update is skipped, set to 0. This works well when the loss landscape is tricky. Lion is not designed by humans, it's designed by Google Brain's search algorithm to find a good performing, high performing algorithm. So the most important trick here is sign operator. Instead of scaling the update by the magnitude of the momentum, it simply takes the sign of the momentum. Interestingly, in Lion, the update is just learning rate times sign of the momentum, and that's it. That's also why it needs small learning rate, because the learning rate is not reduced by anything else later. So we don't want big, huge destabilizing steps. Adam Mini is designed to reduce the memory footprint because the Adam W stores first and second moment of every parameter in the model, which can take a lot of memory. So, in neural networks and models, you can divide parameters by blocks. For example, all parameters in query projection in one attention head. So Adam Mini would store same learning rate for entire block. So the shared learning rate is computed by averaging the second moment estimates within that block. This drastically reduces the number of second moment values that need to be stored, cutting the optimizer's memory usage by up to 50% and allowing for larger batch sizes or all models to fit the same hardware. Muon is a bit tough to explain. So, you know that when we multiply weights with input numbers, the weight matrix, it's like a rotation. It rotates the entire space, entire coordinate system. So we want it only to rotate. We don't want it to stretch things, because stretching matrix, stretching coordinate system is not good. I don't know why. We just want it to rotate. So we make weight update matrices rotate. Muon is typically for 2D weights in the neural network, not for all of the weights. And to understand why is stretching not good, why is only rotation good, there needs to be a lot of math theory. I'm gonna go through that. I don't know yet why, but we use this Newton-Schultz method to approximate division with singular values. I'm not sure. I have a bunch of videos on Muon Optimizer, so you can just search my channel. But we just want to make matrices rotate and not stretch. Cron is a type of second order optimizer. So as I understand, this is second derivative that calculates if the loss surface is concave or convex, so the Hessian matrix. And because Hessian matrix is computationally impossible for large models, they use approximation method. So it uses this Kronecker product to approximate of two much smaller matrices to approximate the big matrix. The optimizer uses preconditioner to rescale the gradients before updating the weights. So this is same as these other optimizers that kind of change weight update matrices. SOAP is shampoo with Adam in the preconditioner's eigenbasis. So it combines powerful second-order preconditioning of an optimizer called shampoo and the efficiency and stability of Adam. So shampoo is a good optimizer, but is computationally expensive. Shampoo is mathematically equivalent to running an Adam-like optimizer, ADA factor, in a different coordinate system, the eigenbasis of shampoo's preconditioner. A bit tough to understand. SOAP leverages this by calculating shampoo's powerful preconditioner less frequently. In between these expensive updates, it performs efficient Adam-style updates within the rotated space defined by the last known preconditioner. This approach significantly reduces computational overhead while retaining most of the benefits of second-order information. I think this one we need to study in a separate video, step by step. So that's gonna be it. 9 optimizers because one I couldn't find information. So that's it for this video. Check out other videos on my channel and see you next time. Let's check out some new AI papers in machine learning and computation and language, which is LLMs. We got a flow matching paper. Flow matching is recently used for generative models, for images. I'm not sure about text, but that could also be done. It's an alternative to diffusion model that relies on ordinary differential equations. So they explain what the problem is and their solution. So if you want to read this, you can read this. If I need this, I will read this, but I don't need it now. We got a paper by Meta, jointly reinforcing diversity and quality in language model generations. Post-training of LLMs often prioritizes accuracy and helpfulness at the expense of diversity. This creates attention. While post-training improves response quality, it also sharpens output distributions and reduces the range of ideas, limiting the usefulness of LLMs in creative and exploratory tasks such as brainstorming, storytelling, or problem-solving. True. We address this challenge with diversity-aware reinforcement learning, DARLING, a framework that jointly optimizes for response quality and semantic diversity. At its core, DARLING introduces a learned partition function to measure diversity beyond surface-level lexical variations. This diversity signal is then combined with a quality reward during the online reinforcement learning, encouraging models to generate outputs that are both high quality and distinct. Okay, so this is interesting paper. I might read it. They also say that encouraging diversity actually makes the models higher quality as well, which makes sense. This paper is for automatic speech recognition for underrepresented languages. This paper is about reinforcement learning from verifiable rewards. They have this PAX method. The proposed method PAX reframes the reinforcement learning problem for LLMs as a supervised task where the model learns to predict the binary correctness reward of its own generated outputs using a cross-entropy loss. So model predicts correctness of its own generated outputs. This approach is designed to overcome the challenges of sparse rewards and training instability found in traditional reinforcement learning with verifiable rewards. Yeah, sparse rewards. With reinforcement learning, you have very sparse rewards. By formulating the problem this way, a single supervised loss function implicitly couples the roles of an actor, the policy that generates text, and a critic, a function that estimates value. A mathematical analysis of the function's gradient shows it naturally separates two parts. One component updates the policy to make correct answer more probable, the actor update, while the other improves the model's ability to predict the reward, the critic update. This unified framework avoids the need for separate models or complex advantage estimation, leading to more stable and efficient training that significantly outperforms strong baselines like PPO and GPO on challenging. I don't know, they always claim they outperform baselines, but every paper outperforms every baseline, which is usually because the baselines are not tuned to their maximum. But maybe this is good, we'll see. Maybe this one actually outperforms. By the way, if you didn't check my latest videos, this is the new FLAIR attention mechanism for linear attention. This is how to make AI researcher, AI scientist for all of the fields. So sorry, this one. And then auto-generated 3D worlds from images. And then this is the trick of how to pre-train LLMs better by letting them predict order of all of the following tokens in a dictionary. So you can check these on my channel as well. And that's gonna be it, and see you next time. 这个模型允许每个人训练模型的一部分，最后再把它们合并，组成一个完整大语言模型。这是一种混合专家 MoE Mixture of Experts 架构。各公司可以在自己的专有或机密数据上训练专属专家，最后所有专家合并组成完整的模型。每个人都会共享一个通用专家，其权重在整个训练过程中被冻结，不会学习或更新，同时各自训练一个专属专家，用来补充通用专家在自己特定数据上的不足。训练结束后，所有专属专家会被合并进同一个大模型，每个专家配一个身份证向量，先把大那批领域文本转成向量，再平均就得到代表该领域的身份证。输入文本也被及时转成向量，与所有身份证比相似度。路由器跳出最像的专家。我现在将附加英文视频，感谢你们的观看。This is crazy new model. It lets different people train different parts of the model on their proprietary data without sharing the data, and then in the end everybody constructs the model. This can also be a way for distributed training where not just one big company has all of the compute and trains the best model, but a lot of people train small parts of the model of one of the experts in the mixture of experts, and then we all combine the big model. Let's learn about FlexMo. Training LLM traditionally requires a massive centralized dataset. This approach creates a significant barrier for organizations that possess valuable domain-specific data but cannot share it due to privacy regulations, confidentiality, or intellectual property concerns. Imagine a hospital wanting to build a medical AI without exposing patient records, or a tech company wanting to use its proprietary codebase without making it public. This is the problem FlexMo is designed to solve. So FlexMo stands for Open Language Models for Flexible Data Use. This new class of models allows for distributed training without data sharing and flexible data use at inference. We definitely need to solve this problem of concentrated AI in a single company with a lot of compute, and then them holding all of the power. So, we have this model, FlexMo, and here are the constraints that it must have. So, data sharing constraints. Standard model training requires all data to be pooled in one location. This is a non-starter for regulated industries like healthcare and finance, or for any organization with sensitive data. Lack of data control. Once a model is trained, it's difficult to remove the influence of a specific data source. This is problematic if data usage rights expire, or if certain data is only appropriate for specific use cases. High cost of collaboration. Methods like federated learning, which also train on distributed data, often require costly and complex synchronized updates between all parties, limiting their practical adoption for massive LLMs. FlexMo solutions are distributed. Data owners train their part of the model locally. Asynchronous. Contributors can train and update their modules independently without needing to coordinate with others in real time. That's the idea. So this is a very good idea. Flexible. End users can include or exclude specific data sources at the moment of inference with no retraining required. So how I imagine it is everybody has its own module, and in the end all modules are combined. That's how I'm imagining it, but let's see if it's like that. Step 2. The architecture, a smarter mixture of experts. FlexMo is built on a mixture of experts architecture. Here's a simple breakdown. So a mixture of experts, instead of one feed-forward network, you have multiple feed-forward networks, and each could be expert in mathematics, history, this, that. So each of the neural networks is an expert in one thing, one domain, and then when language model needs to process some information, it's gonna choose the appropriate expert. FlexMo adapts this mixture of expert concept for its unique purpose. There is one public expert, which is general purpose model trained on a large open dataset, like a filtered version of the web. I can guess where this is going. You have public, single shared expert or multiple, and they are always activated, and then some of the other experts get also activated that are trained with different like organizations and stuff. This is such a good idea. This is such a crazy good idea by them. Each data owner with a private dataset, math, code, legal, trains their own specialized expert, When the model is used, all these experts are brought together. The router's job is to intelligently route a user's query to the right combination of experts. For example, a question about Python might activate the public and code expert. Yeah, that's it. This is such a good idea. I didn't think about this. Public shared expert and specialized experts trained by different companies. And these experts don't share data, and they can be disabled or excluded in inference. Step 3, the training secret, training to coordinate. And by the way, these ALMA models are from Allen Institute of AI. It's fully open source. This is the most critical innovation of FlexMo. How can experts trained in complete isolation learn to work together seamlessly? If each expert is trained independently, their internal representations might diverge so much that combining them produces incoherent results. FlexMo solves this with a clever technique called coordinated training. Start with a public anchor. Every data owner begins with the exact same pre-trained public model, MPub. This model acts as a shared foundation or a common language. Create a temporary two-expert MoE. To train a new math expert, for example, the data owner sets up a temporary MoE model with just two experts. The public expert and it's frozen, so this is the original that we got here, so it doesn't update during training, and the new math expert. The weights here are initialized from our MPub, our public model, but then the weights are also updated during training on the private dataset. Train on private data. The data owner now trains their temporary mixture of experts on their private math data. During this process, the math expert learns to specialize in mathematical reasoning, for example. So by training this math expert alongside the frozen public expert, the math expert learns to fill the gaps and learns to use and learns the math knowledge that this public frozen expert doesn't have. Since every data owner uses the same frozen public anchor, all specialized experts indirectly learn to be compatible with each other because they are all compatible with the same public expert and they adapt to the same public expert. So this is a good idea. I feel like this is like some of those ideas where you don't know if it's going to actually work. But since turns out in this paper, I guess it turns out it worked. Step 4, the router. Merging without joint training. The second major challenge is training the router. Yes, a typical mixture of experts router needs to see data from all experts to learn which one to choose. But in FlexMo setup, no single party has access to all the data. So you need to also train the router to choose the experts. But we are training experts separately. So how do we now add router to all of those experts when we group them together? The solution is domain-informed router that is assembled, not jointly trained. Router embeddings. Each expert is assigned a vector or embedding that represents its domain. The router works by calculating the similarity between an input token and each expert's embedding to decide where to send it. This is good. Smart initialization. To get a good starting point, the router embedding for the math expert is created by taking a sample of documents from the private math dataset, running them through a general purpose text embedding model, and averaging the results. This gives the router a mathematical scent for the expert. So you take a few or bunch of samples from these documents, convert them to vector embedding, and then average all of those vector embeddings to find like average mathematical vector embedding that shows this mathematics, this embedding of this meaning of these documents that this expert was trained on, these math documents. 3. Fine-tuning in pairs. During the coordinated training, step 3, the router embedding for the new expert is fine-tuned. Wait, this is a bit confusing to me as well. The router learns a simple pairwise decision. For this token, should I use the public expert or the new specialized expert? So this is where we are still training the two experts, so each pair individually. It's choosing either public or the specialized. Final assembly. To create the final model, you simply stack the router embeddings from all the independently trained experts. This forms the complete router matrix that can now choose between all available experts without ever having been trained on the combined dataset. So I guess each expert has its vector embedding meaning of the meaning, and we just put all of them, and then router produces a vector embedding, and then we find which one is most similar, and then choose that expert. That's how I understand it. The paper also mentions adding a negative bias term to each specialized expert's score. This is a subtle but important tweak that encourages the router to be more selective, only activating a specialist expert when it's highly confident and defaulting to the general public expert otherwise. Okay, so we want to make it only select this if it's highly confident and the general otherwise. And then during inference, if you want to exclude some information, some expert, it's very easy to just remove the expert and somebody's proprietary information, let's say. So they tested this FlexMo model versus this base model, the general expert model, and versus any of these experts. So the whole combined model outperforms any single expert. And for this to make sense, I believe they used same amount of compute and made it fair. They also tried to figure out if it's possible to extract this proprietary data from the experts, and they find it very, very difficult to extract proprietary data from the model from the experts. So it's difficult for somebody to steal the proprietary data that it was trained on. Check out other videos on my channel and join my Discord. A link below the video. This is crazy new model. It lets different people train different parts of the model on their proprietary data without sharing the data, and then in the end everybody constructs the model. This can also be a way for distributed training where not just one big company has all of the compute and trains the best model, but a lot of people train small parts of the model of one of the experts in the mixture of experts, and then we all combine the big model. Let's learn about FlexMo. Training LLM traditionally requires a massive centralized dataset. This approach creates a significant barrier for organizations that possess valuable domain-specific data but cannot share it due to privacy regulations, confidentiality, or intellectual property concerns. Imagine a hospital wanting to build a medical AI without exposing patient records, or a tech company wanting to use its proprietary codebase without making it public. This is the problem FlexMo is designed to solve. So FlexMo stands for Open Language Models for Flexible Data Use. This new class of models allows for distributed training without data sharing and flexible data use at inference. We definitely need to solve this problem of concentrated AI in a single company with a lot of compute, and then them holding all of the power. So we have this model FlexMo, and here are the constraints that it must have. So data sharing constraints. Standard model training requires all data to be pooled in one location. This is a non-starter for regulated industries like healthcare and finance, or for any organization with sensitive data. Lack of data control. Once a model is trained, it's difficult to remove the influence of a specific data source. This is problematic if data usage rights expire, or if certain data is only appropriate for specific use cases. High cost of collaboration. Methods like federated learning, which also train on distributed data, often require costly and complex synchronized updates between all parties, limiting their practical adoption for massive LLMs. FlexMo solutions are distributed. Data owners train their part of the model locally. Asynchronous. Contributors can train and update their modules independently without needing to coordinate with others in real time. That's the idea. So this is a very good idea. Flexible. End users can include or exclude specific data sources at the moment of inference with no retraining required. So how I imagine it is everybody has its own module, and in the end all modules are combined. That's how I'm imagining it, but let's see if it's like that. Step 2. The architecture, a smarter mixture of experts. FlexMo is built on a mixture of experts architecture. Here's a simple breakdown. So a mixture of experts, instead of one feed-forward network, you have multiple feed-forward networks, and each could be expert in mathematics, history, this, that. So each of the neural networks is an expert in one thing, one domain, and then when language model needs to process some information, it's going to choose the appropriate expert. FlexMo adapts this mixture of expert concept for its unique purpose. There is one public expert, which is general purpose model trained on a large open dataset, like a filtered version of the web. I can guess where this is going. You have public, single shared expert or multiple, and they are always activated, and then some of the other experts get also activated that are trained with different organizations and stuff. This is such a good idea. This is such a crazy good idea by them. Each data owner with a private dataset, math, code, legal, trains their own specialized expert, When the model is used, all these experts are brought together. The router's job is to intelligently route a user's query to the right combination of experts. For example, a question about Python might activate the public and code expert. Yeah, that's it. This is such a good idea. I didn't think about this. Public shared expert and specialized experts trained by different companies. And these experts don't share data, and they can be disabled or excluded in inference. Step 3, the training secret, training to coordinate. And by the way, these Olmo models are from Allen Institute of AI. It's fully open source. This is the most critical innovation of FlexMo. How can experts trained in complete isolation learn to work together seamlessly? If each expert is trained independently, their internal representations might diverge so much that combining them produces incoherent results. FlexMo solves this with a clever technique called coordinated training. Start with a public anchor. Every data owner begins with the exact same pre-trained public model, MPUB. This model acts as a shared foundation or a common language. Create a temporary two-expert MoE. To train a new math expert, for example, the data owner sets up a temporary MoE model with just two experts. The public expert, and it's frozen, so this is the original that we got here, so it doesn't update during training, and the new math expert. The weights here are initialized from our MPub, our public model, but then the weights are also updated during training on the private dataset. Train on private data, the data owner now trains their temporary mixture of experts on their private math data. During this process, the math expert learns to specialize in mathematical reasoning, for example. So by training this math expert alongside the frozen public expert, the math expert learns to fill the gaps and learns to use and learns the math knowledge that this public frozen expert doesn't have. Since every data owner uses the same frozen public anchor, all specialized experts indirectly learn to be compatible with each other because they're all compatible with the same public expert and they adapt to the same public expert. So this is a good idea. I feel like this is like some of those ideas where you don't know if it's going to actually work. But since turns out in this paper, I guess it turns out it worked. Step 4, the router. Merging without joint training. The second major challenge is training the router. Yes, a typical mixture of experts router needs to see data from all experts to learn which one to choose. But in FlexMo setup, no single party has access to all the data. So you need to also train the router to choose the experts. But we are training experts separately. So how do we now add router to all of those experts when you group them together? The solution is domain-informed router that is assembled, not jointly trained. Router embeddings. Each expert is assigned a vector or embedding that represents its domain. The router works by calculating the similarity between an input token and each expert's embedding to decide where to send it. This is good. Smart initialization. To get a good starting point, the router embedding for the math expert is created by taking a sample of documents from the private math dataset, running them through a general purpose text embedding model, and averaging the results. This gives the router a mathematical send for the expert. So you take a few or bunch of samples from these documents, convert them to vector embedding, and then average all of those vector embeddings to find like average mathematical vector embedding that shows this mathematics, this embedding of this meaning of these documents that this expert was trained on, these math documents. 3. Fine-tuning in pairs. During the coordinated training, step 3, the router embedding for the new expert is fine-tuned. Wait, this is a bit confusing to me as well. The router learns a simple pairwise decision. For this token, should I use the public expert or the new specialized expert? So this is where we are still training the two experts, so each pair individually. It's choosing either public or the specialized. Final assembly. To create the final model, you simply stack the router embeddings from all the independently trained experts. This forms the complete router matrix that can now choose between all available experts without ever having been trained on the combined dataset. So I guess each expert has its vector embedding meaning of the meaning, and we just put all of them, and then router produces a vector embedding, and then we find which one is most similar, and then choose that expert. That's how I understand it. The paper also mentions adding a negative bias term to each specialized expert's score. This is a subtle but important tweak that encourages the router to be more selective, only activating a specialist expert when it's highly confident and defaulting to the general public expert otherwise. Okay, so we want to make it only select this if it's highly confident and the general otherwise. And then during inference, if you want to exclude some information, some expert, it's very easy to just remove the expert. and somebody's proprietary information, let's say. So they tested this FlexMo model versus this base model, I mean the general expert model, and versus any of these experts. So the whole combined model outperforms any single expert. And for this to make sense, I believe they used same amount of compute and made it fair. They also tried to figure out if it's possible to extract this proprietary data from the experts, and they find it very, very difficult to extract proprietary data from the model from the experts. So it's difficult for somebody to steal the proprietary data that it was trained on. Check out other videos on my channel and join my Discord. A link below the video.
Flex Attention, created by Meta, is an AI research tool that lets researchers create a lot of different attention mechanisms and without sacrificing performance of handwritten kernels, so they are fast. So it's a tool to create quickly, fast and efficiently and a lot of different attention mechanisms. This addresses the problem of software lottery, where the feasibility of a new model architecture is dependent on the availability of an existing optimized software kernel, or you need to know how to write it yourself, which is also difficult. So you just need to write a few lines of code in PyTorch to create a new attention mechanism, and it will all be compiled into efficient fused kernels that run fast on GPU. You don't need to know how to write it yourself. This approach not only accelerates the research and development cycle of a single person, but also democratizes the ability to explore novel attention strategies for a lot more people. The key of Flex Attention lies in two key modular components: score mod. This enables modification of attention scores after the query key dot product. And mask mode lets you create different attention masks. For example, causal mask for decoder models and sliding window attention. Let's see some code examples. So let's see how to implement causal mask. So we use this mask mod to return true if query is greater or equal to the key. So query can only attend to keys that have same or lower index. So query index is greater than key index. So it can only attend to previous tokens, not future tokens. And we will create this block mask, create block mask from our causal mask mod to just for some optimizations, and then apply flex attention with the block mask. Then we have sliding window attention, where queries can attend to just the fixed window of previous keys, previous positions. So let's say last 10 positions, last 100 or last 1000 positions. So the condition here is that, of course, queries can attend only to previous and the same position keys, and only up to a certain size, window size in the past. And the rest of the code is same. Let's see this relative position bias. So this is just gonna modify the attention scores based on the distance between the query and the key tokens. So it will apply penalty if the distance between tokens, the query and key, is longer. Here we will use score mod, not mask mod. This will let us directly manipulate the attention score. The function in this case is called alibi bias score mod. We calculate the distance between the index of query and key, and then the bias is minus distance times this slope, 0.1. And then return the score, the current score plus bias, which will be some negative number. So we subtract a little bit, and the longer the distance, the more we subtract from the score. So this will make it pay less attention to tokens that are further away. Another use case is you can put multiple documents into a single sequence, but you would only let tokens attend tokens in the same document because other documents are unrelated. So you can gain nothing by attending to other documents. You get no information You just get useful information from the same documents information. So here we want to mask just the current document and have causal attention, so only look at the previous tokens. So we will create separate mask mode functions and combine them with AND operators, so both of them must be true. This is one example. So we do document IDs like this. So first document has these 3 tokens, second document has these 5 tokens, and now we just combine that with our causal mask. You can check this if you want to understand like how it works, but the idea, like I think you get the idea. We just use AND is causal and same document. That would be the quick intro for flex attention. You can use many different kinds of masks and score manipulations and design attention mechanisms quickly. So check out other videos on my channel and see you next time.
Let's see how different optimizers work in large language model pre-training and other types of neural networks as well. We will understand how to find real speedups in the real world. So how to find optimizers that actually make LLMs better in the real world, not just with experiments that were not well set up in research papers. So first, you need to find the best possible setting for each optimizer. A lot of papers don't find the best settings for Adam W, and then they claim they have better optimizer, but you need to find the best settings for each optimizer. In this case, they're gonna train 130 million parameters, 300, 520, and 1.2 billion parameters. Then you need to select your optimizers that you will compare. So Adam W good base and Adam W Lion, an optimizer discovered through symbolic search. And then they will check other optimizers like Mars, Muon, Cron, etc. For each optimizer, you need to test a lot of a big different range of hyperparameters. For this, you can use coordinate descent approach over a grid of possible values. They include learning rate, weight decay, warm-up steps, beta and beta 2 for Adam style optimizers, epsilon for numerical stability, maximum gradient norm, batch size. They are also varying amount of data for a single model size. So there is a lot experiments to do. I don't think we should do like every with every, but there is some rules how to do it. We can do rough search first and then see which hyperparameters are most sensitive. Changing them has a lot worse or better models. It's also important to focus on when you scale data, how like different hyperparameters react to scaling data. For example, learning rate is usually sensitive to scaling data. And scaling batch size, you need different learning rates for different batch sizes. And also warm-up schedule is also sensitive to scale. Different scales require different hyperparameters. And so as we scale the model size, the data size, we want to use only the most sensitive hyperparameters. So we don't want to do so many ablations, so many experiments with big models, big data sizes. We start with small models, do more experiments, and then find sensitive ones. And then we scale the data and model and only test those fewer sensitive hyperparameters. The way you measure speedup is how much data, how much less data the new optimizer needs to see in comparison to, for example, Adam W, which is the most popular one. So we want to surpass that. So if it reaches the same loss with 20% less data, then the speedup is 1.25. But you can also measure time but we are constrained with data in large language models. So we have a lot of compute, but we don't have enough data. So I guess measuring for data, squeezing out the best performance from data is most important. And we have compute, like we can use more compute if the optimizer will give us better results for less data. In the final phase, we want to predict how, what are optimal hyperparameters for even bigger, massive models without necessarily needing to train all of those massive models to search. So you find optimal, for example, learning rate for every size, and you just extrapolate. So for example, optimal learning rate, if you double the model size, you need to increase learning rate or decrease learning rate by 20%. So that's how you can calculate. These scaling laws are then used to predict optimal hyperparameter settings for even larger models and data volumes that were not part of the initial sweeps. So if you fine-tune properly the hyperparameters, then the biggest speed up over AdamW is 1.4%. I don't know which optimizer, but not the 2x that we claim for MuOn optimizer. So maybe MuOn optimizer. But if you fine-tune the AdamW, then the speed up is just 1.4%. This is good because it means you can extract more juice from just fine-tuning optimizer or hyperparameters. Optimizers that use more sophisticated methods for preconditioning the gradients, such as MuOn, SOAP, and cron, generally outperform simpler methods. So it's good to somehow process or fix the update weight matrices before we apply them. That's what MuOn does. Make them not stretched, make them just rotate the space, not stretch the space. So they are preconditioning the gradients. Maybe we can discover some new ways to precondition gradients. There is no one optimizer that's best. For example, MuOn is good with less data, while SOAP and cron are good if you have a lot more data for the same model size. Study shows that optimizers are very sensitive to hyperparameters. Even a bit misconfigured one hyperparameter will eliminate all of the entire speedup that we are supposed to have. And even during the training, the performance of different optimizers can change based on hyperparameters. For example, during learning rate decay. Therefore, it's essential to evaluate performance at the end of the full training schedule. We have new model, multimodal R4B. R4B is a billion parameter multimodal large language model designed to be both powerful and efficient. Its key innovation is an auto-thinking capability, which allows the model to automatically decide whether to use a complex step-by-step reasoning process, thinking, or give it a direct, concise answer, non-thinking, based on the difficulty of the user's query. To achieve this, they use a process that involves two steps: by-mode annealing and by-mode policy optimization. By-mode annealing, teaching the model how to think and not think. The first goal is to create a base model, R4B base, that is proficient in both thinking and non-thinking modes across a wide range of topics. They needed a massive dataset with examples correctly labeled as either requiring reasoning or not requiring reasoning. Creating this manually is impossible. Instead, they developed a clever automated strategy. They used a very powerful existing model, Qwen 2.532B-VL, as an automated annotator. For objective questions like math, they used offline hard mining. If the powerful model failed to answer a question correctly multiple times, the question was labeled hard and assigned to the thinking dataset. If it answered easily, it was labeled easy and assigned to the non-thinking dataset. For subjective questions like describe this image, they use prompt engineering to have the model judge the complexity of the query. So they just judge it with prompt engineering. Training protocol. The model was trained on this mixed dataset, thinking samples, formatted as a think, detailed reasoning steps, and then close think tags and final answer, and non-thinking samples. They just have this think and close think in the beginning without anything in between, and then final answer. The tags are present but empty, teaching the model the structure for a direct response. So the stage 1 produced the R4B base, and it was capable of performing both modes, but it was biased towards not using thinking. So they call this thinking entropy. Then stage 2, by-mode policy optimization, teaching the model when to think. The problem with standard reinforcement learning is if you just reward correct answer, then model would always use thinking because it would just use more compute to get the correct answer. So they use this by-mode rollout. So this is the trick. For each input query during training, the model is forced to generate two separate responses, one in thinking mode and one in non-thinking mode. Both responses are then evaluated by the reward model. They noted in paper that they just needed a simple rule-based reward function for mathematical domain, and this surprisingly generalized well to other areas. The model's internal policy is then updated to favor the mode that led to a higher reward for that type of question. We see here it outperforms Qwen 2.5 VL 7 billion parameters, outperforms some other models as well. Here you see how only thinking mode has a lot more tokens than this auto thinking. And so this is deciding if it should use fewer tokens, just like the non-thinking mode, if it's easy, or use more tokens like thinking mode, if the questions are hard. That will be it for this video. Check out other videos on my channel, and see you next time. A new massive survey of scientific large language models. How LLMs are used in science. So there is 94 pages and it cannot be done justice in one video, but this video is mainly to inspire you and to teach you about this so you look into this yourself. The paper argues that the future of AI in science isn't just about bigger models, but about a deeper co-evolution between the AI systems and the scientific data they are built on. Yes, you can build LLMs that are more adapted, have tokenizers and data adapted to scientific discovery. So they would be better for science. LLMs are very sensitive to the type of data and the training they've been exposed to. It reframes the entire field through a data-centric lens, moving from the foundational data that models learn from to the advanced AI agents that will one day conduct research. So all the way from data to agents and everything in between. Part 1, the foundations, a new way to think about scientific data and knowledge. Before diving into the models, the paper establishes two crucial frameworks for organizing the complex world of scientific information. Finding 1, a unified taxonomy of scientific data. The authors argue that scientific data is far more complex than the text and images general-purpose LLMs are trained on. They propose a taxonomy to classify this data, highlighting the unique challenges each type presents. Textual formats. This is the bedrock, including everything from scientific papers and textbooks, archive PubMed, to lab notebooks and experimental protocols. Visual data. This is a vast category spanning multiple scales and modalities. Instrumental imaging, capturing physical reality from the atomic scale electron microscopy to the cosmic Hubble telescope images. Medical imaging, specialized formats like DCOM and these others for X-ray, MRI and CT scans. Diagrams and plots, abstract representations of concepts like molecular structure diagrams, circuit schematics and data plots, which are crucial for scientific communication. Symbolic representations, this is the language of science itself. So for molecules, we have strings like SMILES, CC0 for ethanol, or selfies that encode molecular structures. Crystals, CIF files that describe the 3D atomic arrangements in materials. Equations, mathematical formulas that represent physical laws. Structured data, organized data in databases, tables, and knowledge graphs, like for materials or genes. Time series data like EEG, brain signals, gravitational waves, weather measurements. And this other type of weird data that I don't understand, like DNA, RNA, protein stuff, and etc. Key takeaway, Sci LLMs must be able to speak all these languages, not just English. They need to understand the syntax of the SMILES string, the spatial logic of the CIF file, and the meaning of peaks in a spectral plot. Finding 2, a hierarchical model of scientific knowledge. And by the way, as I said, LLMs are highly dependent on the way of training them. We can create tokenizers, specific tokenizers for all of these. And so they understand EEG, understand DNA, RNA, and then train them on that data. All of the LLMs right now, GPT-5, Grok, this, that, they look similar, but they're actually just similar because they're trained in the exact same way. But LLMs can be trained in completely different ways to be completely different. So the paper says that scientific knowledge isn't a flat dataset database of facts. It's a hierarchy where information is progressively transformed into deeper understanding. This framework, inspired by the DIKW pyramid, at the bottom you have data, then information, then knowledge, then wisdom. So their framework is based on that pyramid, and it helps to explain what we expect AI to do. The paper has 5-level knowledge hierarchy. Factual level: raw objective data from experiments and observations. Image, DNA sequence, temperature readings. A theoretical level: the laws, principles, and models that explain the facts, like Newton's law, theory of relativity, central dogma of biology, etc. Methodological and technological level: the tools and procedures used to get from facts to theories, for example, CRISPR-Cas9, experimental protocols, statistical methods, machine learning algorithms. Modeling and simulation level: use computational models to simulate reality, test hypotheses, and make predictions. For example, climate models, molecular dynamics simulations. Insight level: the highest level representing true scientific discovery and breakthroughs, often by connecting disparate fields or identifying anomalies. Example: connecting information theory to biology to create bioinformatics. Key takeaway: a truly intelligent scientific LLM must operate across all these levels. It should be able to process raw factual data, reason with theoretical models, understand the methodology behind the data, run simulations, and ultimately help generate novel insights. Part 2: the landscape of scientific LLMs and their data diet. The survey provides a panoramic view of existing Sci LLMs by analyzing over 270 training datasets and 190 evaluation benchmarks. Different architectures of these scientific LLMs were with transfer learning, this is evolution. So in the beginning, transfer learning, then scaling, so models like Galactica, then instruction following, models like Llama Gene for biology, and agentic science, which is the latest evolution. Agents that are developed to autonomously use tools, plan experiments, and perform research. So the secret sauce is not the architecture. You can use Llama, Qwen, Mistral. The secret sauce is the specialized data used for continued pre-training and instruction fine-tuning. Because in the beginning, or in the pre-training, these models, they just learn generally about the world and language. And then you can use other scientific data for continued pre-training. There are some issues in creating these models. For example, when model is trained on clean simulation data, it can struggle on the messy, noisy real-world data, like with physics simulations. Some bottlenecks for these scientific LLMs are scarcity of experimental high-quality AI-ready data. So there is over-reliance on text and simulations. This is maybe a research topic on how to generate this scientific data more and easier. The text modality bias: science is multimodal, but our data is mostly text. Models learn about experiments from the text and not from the experiments themselves. Also, data is the static knowledge. It doesn't capture evolving experiments and hypotheses and how science evolves. So LLM struggles to learn that. They just learn kind of facts inside of the data, text data. Data latency: so when some new discovery is invented, there is some time for this discovery to end up in the training data for the LLMs. So LLMs training data is always lagging behind the real world cutting edge science that it's intended to be used for. And then most scientific data and papers are not formatted in AI ready way. So there is a perfect way to format something for an LLM. Every file, it has its own perfect way, which we need to figure out how to convert human readable files to perfect LLM files. But there are ways to overcome all of these issues with scientific agent. AI can be used to rewrite data, to collect new data, etc. And agents can also be used in the research, like plan, use tools, collaborate, self-evolve. For example, there can be multiple agents principal investigator, data analyst, experimentalist. We went through a lot of these subtitles here: taxonomy, hierarchy, key challenges. So you can dive deeper here. You can also learn more how LLMs are used in different fields like chemistry, physics, etc. I think it's really good idea to train LLMs specifically for science from scratch, because they will be different than these LLMs. But also there is this thing called the bitter lesson. It means that just giving LLMs more compute and making in more data makes them better than specifically training it for science or some specific like clever trick, which is sometimes true, sometimes not true. So I'm not sure if making just LLMs bigger with more compute, general LLMs will perform better or worse than LLMs made for scientific discovery. But maybe if we use same amount of compute on scientific LLMs as in general LLMs, maybe then scientific LLMs will be better for science.
Hello guys, I implemented this mixture of experts. In this llm.py file, if you just run this, there is a benchmark for both classic feed-forward and mixture of experts. So in this case, almost 30 million for regular feed-forward, 54 million parameters for mixture of experts, but MoE has a lot less active parameters. It trains more, so I think the implementation is good, but I want your feedback, and maybe you can help me do it more efficiently and maybe even discover some bugs if there are any. You can create pull requests, but you can go here and copy this into ChatGPT and learn how I implemented it and how it works. Mixture of experts achieves lower loss, but also trains a lot longer. I'm not sure why. Both train for the same amount of steps. Anyways, I'll look into this. So you can use this to self-study. I want to do research on this. I want to do experiments. I want to try, for example, no computation expert that just lets simple tokens pass without any computation. And I want to try many other experiments. So this is good for research. If you're interested, join the Discord. So here we have all of the ideas and we do research together. And in general, we're going to be publishing AI papers. In other news, I tried for my feed-forward network, not mixture of experts, but just feed-forward, I tried Silu and Swiglu, and for some reason Silu worked better. Maybe because the model is small, or I trained only a little bit, maybe too little. Maybe if I train for longer, Swiglu would work, because Swiglu is known to work better than Silu. Also, I fixed the bug with rotary embeddings. Now this is all of the entire implementation of rotary. Before it was a lot bigger, it was huge. Now I'm just using this rotary positional embeddings from PyTorch torchtune.modules. Anyways, give me your ideas below on how I can test this. I want to make it mixture of experts, how I can test this, what experiments research I should do. And help me uncover and find any bugs, if there are any. That's it for right now. It's a quick video, and see you next time. You can check other videos here on my channel, and see you next time.
Hello guys, I'm starting an AI research laboratory, but it's gonna be different than your classic lab. So this one is gonna be completely open source, so we will do everything in public. We are writing our first paper here on Discord, and I'll leave the link below for this GitHub repository that we are working on. So we are analyzing MuP Optimizer in an LLM that we coded ourselves, and this is still a work in progress. I know this name is kind of weird, Open Superintelligence Lab, but this is the only name that portrays what we want to do. So we want to build everything fully in open, and that anybody can contribute. And I know the name sounds a bit pretentious, but it is what it is. Other names just don't portray what we want to do. I want somebody to read our paper and to get curious, okay, what is this Open Superintelligence Lab? And then we want people from everywhere to just contribute to our research, from universities, labs, everywhere. We currently have some PhD students and one Meta senior software engineer and other people who are contributing. All of the labs, they have investments, they pay salaries, and then there is just a few people who can get into those labs. So that's the problem. So I think there is a huge market for everybody who wants to contribute to AI without needing to become expert and get a job at the company. and the companies are also keeping everything closed source. So it's questionable how much somebody is contributing as opposed to open sourcing their work. So there is absolutely no way for us to make money. So nobody wants to invest in this. We're not selling anything. So there is no way anybody will give us money. So this is open source research, scientific research meant for people to do in free time, or me. I'm gonna do this full time, and I'm gonna rely on maybe some tips, or I'm gonna rely on some grants. I'm gonna apply for some grants later when I have research, or I can go like get a master's degree or PhD. Maybe I'm thinking about that as well, and then just work on this. So this project is pure contribution to science and advancement of technology and for society, for humanity, for the world. I think we can have a lot more impact onto AI research and science than any other closed lab, simply because we are open sourcing. Even if they have better research, if they're not sharing it, they're not accelerating the rest of people, rest of researchers, and we are. So we are open sourcing everything, not just like maybe some models or some pieces of code while keeping other pieces of code secret. We are open sourcing absolutely everything and doing everything on Discord, on GitHub, etc. So you can come to the Discord and this channel analysis of muon in LLMs, and you can start contributing to this paper. And I'm gonna have more research projects going on right now. I mean soon. So I can put you on this paper here if you make a significant contribution. So you write a piece of code, you do some results. So maybe you draw some graph, chart. I think it's not difficult. I think you can vibe code some charts and then just tell the AI to learn, to explain what it learned from these charts, and maybe you think about it a bit, and then you just contribute this, and you can end up on the paper. I'm gonna put everybody who makes this kind of contribution. I think it's not difficult at all. We will do research on free Google Colab or Kaggle GPUs, and I got Novita AI giving me some free compute, so maybe we'll get more free compute from them, from other places. Maybe we'll have a bunch of different places because we will use all of that free compute. Everybody in the world will be researching here. No barrier to entry. So I personally could also get a PhD, and then I could just work on this project, but I need to find a professor who's gonna let me just work on this project, and maybe they can mentor. So maybe this can be same situation for you, or you can do this in free time, because again, like there is nobody who's gonna give us money or invest. We're not selling anything. This is pure science, pure contribution to development of the technology and science. And I think once people see that they don't need like gigaclusters of compute to contribute to science, then a lot more people will start. I had a guy, he's young, and he was just training on like a CPU. He invented his own optimizer. It's not the best optimizer in the world, but what I'm trying to say, just on a CPU, invented a new optimizer. So we don't need like billions of dollars of compute to do science. We can do this. And other companies will give us compute and donations and grants and governments and everything. Other thing is, we don't have investment, we don't have expenses. It's impossible for us to fail. I'll be doing this for the next 50 years. I tried everything. I tried entrepreneurship, business. I don't care. I just want to do this. So what I'm gonna eat in 6 months, I'm not sure yet, but I'll just do this probably for the rest of my life. As I've been doing this for the last like 2 years, and I don't want to get a job. I don't want to do anything else. I just want to do this. For me, getting a job is like somebody putting me in prison and preventing me from contributing to science. Maybe if somebody wants to pay me to do all of this, but this would be like PhD or grants or something. If you're a professor or you want to take me as your PhD student, please email me. And also, I'm going to be doing thesis for ending my bachelor's degree right now. And we got a really good math professor who's going to mentor me. And I'm going to publish open source everything. I'm going to do a thesis here about muon optimizer or optimizers or something. So everything will be open. I think that's all I had to say. And guys, I need your help. I'm not an expert researcher yet, maybe in the future, but I need your help, suggestions, ideas, and come hang out with us. We got like some smart people in the Discord, and give your ideas, give your contributions, and I'm gonna start new projects. And you can also start your own community projects. You need to lead them. So people are gonna look at what you do and they're gonna help you contribute. You can do your research papers here, or if you know some PhD students, tell them to do their research papers here in this Discord. We're gonna all contribute. I'm gonna personally contribute, and we're all gonna help advance science. Until the next time, join us, and I'm gonna be making like more videos today, tomorrow, just updating on the research on new projects, what I've done, the new insights I gained and everything. So see you next time.
Hello guys, I made a fully autonomous AI researcher. So this research report was fully done by AI 100%, multiple LLMs working together and evaluating, ideating, coding, and this is the whole no, that's some errors, but here we have whole research, all of this data. First of all, for LLMs, you want to have some setup, some code to start from. So I have my mixture of experts LLM that I coded. I have a video, just type on my channel, I coded mixture of experts LLM, and you can check this. I'll leave the link below to this so you can see all of these files. And then I told it to design some experiments based on this code, so to modify it. But as I said, with LLMs, you don't want to start from nothing. You want to give it something to work with. So here, I have this research paper, and I just took some of the ideas here. So about, I just copied like a bunch of like stuff here, some this part, some ideas about experts in mixture of experts, and I gave it here in the research prompt. So this is the part I just copied it. I have some prompt here. You can check all of this. So this is the copied part from the paper. And then these are just, I need to improve this prompt, by the way. This was just a quick pilot. And I also have a system prompt. So this is just about how to design research. I want to make it short. So every experiment 2 to 10 minutes on 1x4090. We can change all of this. And then I have multiple different LLMs talking to each other. So I have proprietary Gemini, and I have Kimi K2 from September, the latest one a few days ago. And I just have them like starting here from Gemini first. So this is going to generate research plan. It's going to be this research plan here that you see. So this is what Gemini outputted. So all of this research plan. And then second, we have Kimi. This is hosted on Novita. I find it cheap there. I like it. I also like their GPUs. You see here, you have all of these models. I use this one, Kimi K2. You have price. I really like. Well, I'm gonna use more models from here as soon as I'm gonna just keep improving this project. Different LLMs have different ideas. They're like different people with different ideas. They can provide different critiques. And you know that every LLM, I think it prefers its own. So every LLM thinks it's right. So you need different LLMs to kind of challenge each other and bring different ideas to the table. I'm gonna maybe use DeepSeek v3.1 and OpenAI GPT OSS, maybe GLM, or I'll see. Also, you have a few calls on Gemini 2.5 Pro for free every day. So you can make sure you use that. So you see, I want Kimi to take the response from Gemini, the plan, and look if the experiments are unfair, to check for bugs, for missing controls, overstated claims. I'm gonna change this. This is AI generated, so I'm gonna improve this. So then I have critique analysis. So you know, sometimes LLMs can generate like too much critique, bloated critique. I don't want bloated critique. So even the critique, I'm gonna analyze it. But what all of this is doing is basically letting LLMs think and agree. And I'm always telling it, like, don't change too much, don't do too many things, like write just a few things. I'm gonna say that I'm gonna improve these prompts as well. And then at the end, I have 4-step Gemini again. This is gonna be final plan. And so this will get followed, whatever it is. So maybe we're gonna change this system, but for now this works. I wanna add more LLMs here. I then gave the final plan to Grok Code Fast 1. So I find this model best because it can do everything other models can do when it comes to AI coding. I find it very good for AI coding also, but it's a lot faster. So I don't need to like forget about it, go do something else. It's so fast. I can just wait a few seconds, it will finish. And also there was 1 or 2 times where Cloud Sonnet couldn't do something, and this Grok Code Fast did. So maybe it's even better. Maybe they trained it for AI coding, AI research in particular. Maybe XAI wants to use it to do AI research as well. And I feel like Grok Code Fast is what will enable this autonomous AI research, because Sonnet is too expensive, Opus especially. And other models are, even GPT-5 is too expensive, and Gemini. But this is like 10 times cheaper than Gemini GPT-5, so cheap. 20 cents per million input tokens and $1.5 for million output tokens. And it's as good as coding at these frontier models, maybe even better, maybe a bit worse, but 10 times cheaper. So that's crazy. This is the reason I can now do this autonomous AI research. We have a really good coder that's very cheap and fast. I ran the experiment on Novita's GPUs as well. Look at these prices, 18 cents, so 50% off if you choose spot billing here. So this is, I think, the cheapest on the market. They even have Blackwell 200, the latest one, just $1.90. But for now, I'm just gonna use these two, 5090 and 4090, and especially 4090. And I can just run multiple of them and let my AI just like run multiple AI research instances at once. At the end, after the experiment has been done, you can prompt some AI to write a report, a tutorial, analysis. So tutorials, I think, are really good because it's explained step by step like this. In this experiment, we added some stochastic noise to routing. So when you're routing tokens to experts, you make it a little bit random. And then does this help? The result is no, it doesn't help, which is actually also a result. So negative result is also a result. Okay, this doesn't help. Now we know this. Now other people will not waste time trying this. But also, this is the thing, I just ran it for like 1.6 minutes. This was just a test. So this is not enough. So we don't actually know this. I need to write this here. So we need to run this on for more time, train for more. But I really like this setup, and now I feel like I'm finally getting to understand how LLMs work and how to use them to do things autonomously. So first you need to start from something, like you need to have a code for your large language model or diffusion model. It can be just base, any type of code. And then you need to reference some paper or some human written ideas, and then let LLM choose or get ideas. It can be even different ideas, but just you need to give it some base to think from. So give it a chunk of paper, and then use different LLMs to talk to each other, and different LLMs bring different ideas, different capabilities, and they kind of fight against like some bias that's gonna make like a mistake. Also, multiple calls, multiple LLMs basically allow for higher output token window. So if one LLM uses all of the output tokens, then you call it again for critique, for thinking, for different LLMs, so you just have more output tokens to think. You are scaling test time. And then Grok Code Fast is really what enabled this autonomous research, because it's very cheap. It's very cheap, so I don't need to worry about price, I think, anymore. So I can just run it. And it seems to be as good or almost as good or even better than Sonnet, so probably not better, but it's very good for this AI research. So it can just code, it can work, it can fix its own bugs and implement code. For the future, I'm gonna improve my prompts and design and architecture, and I predict that the more LLMs, open source LLMs, get better, the more we will just let them run on autopilot. So I feel like the more they get better, the more we will just use them, and there will be like return on investment and everything. So in a year, I might be having like 10, 20, 50 of these agents doing different research. And the future idea also, we need to generate like these research reports and then put them all into like a folder or some, and then maybe summarize each research in one document. One document contains summaries of every research, so future research that these LLMs can use previous research they did. So they just read the entire document that contains all of the summaries for every research, and then they can decide which research to choose, to analyze, to get all of the report, to analyze more carefully, to implement, to learn from. So it's like a database of research. And this is effectively like memory for LLMs. and they have now big context windows, so they can just build their own research. And the goal would be like a better LLM. So the goal, there could be like a big ultimate project. It could be like more efficient, better large language model, like mixture of experts. So then it builds research, does different research, maybe starts different agents. This is so interesting. And LLMs are so cheap now, and they are so good. So this really opened up the possibilities for autonomous AI research.
New paper for diffusion models is actually quite a good idea to make diffusion models faster. In diffusion models, we have a sentence. The capital of France is mask, 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 mask. So let's say in this case, we want to predict letters, Paris. In the first iteration, it can predict P-A-R-U-S. In the next iteration, it can find that this U is low confidence, so predict, so mask it again, and then try something else, I. But in reality, it will predict a lot more, in a lot more steps. It will predict sentences in maybe 100 steps, 100 iterations, every time masking some of the predicted tokens back and then predicting them again. So this paper's figured out it doesn't actually need so many steps. It doesn't need it. Instead, let the model stop early when it's confident that it has the answer. So don't have it for 100 fixed steps. If it's confident at 20 steps, let it just end there. So how do we measure this confidence of the model? So for each of these places, for example, U, it will take entire vocabulary of all possible tokens and assign probability for how likely is each token to be here at this spot. This is how it already works. This is the architecture that's current. This is not from the paper. This is how it works. For each place, it just assigns a probability for every possible token to be at that place, at that mask. And to know if model is confident, what they do in this paper, they check the probability of the most confident, highest probability token versus second highest probability. If the gap is large between first and second, then model is very confident that that first token is there. It has a lot higher probability. But what they do is to decide to early stop entire process. They take average confidence for all of the tokens. And if the average confidence, average distance between first and second most probable tokens is high on average, above some threshold, then they stop the generation process. And it maybe reduces their time by a lot, maybe 2 times, 3 times, or 75%. Or so when the average confidence is high enough, confidence gap is higher than threshold, this mechanism makes the call to stop. And they just take whatever the current generation is and they make it as the final. And next, we will just go step by step, like reading this from the beginning, but you already understand the situation. But now we'll just go step by step, like summarizing the paper. The core problem with diffusion language models. So we know that diffusion models start with a sequence of masked tokens and iteratively refine them in parallel until a coherent sentence emerges. Think of it like a sculptor starting with a block of stone and gradually carving out the final statue. The problem, while diffusion language models have the potential to be faster because they can decode many tokens at once, parallel decoding, the paper points out 2 major issues that make them slower in practice. High computational cost. Their bidirectional nature, every token looks at every other token, is computationally expensive and doesn't easily support optimizations like KV caching. Many refinement steps. To get high quality text, they need to go through many rounds of prediction and remasking, which takes a lot of time. So they predict the masked token to a token, and then some of those tokens, for example, ones that were least confident, they mask them back, and then they predict them again, and then a chunk of those that are least confident mask them back, etc. The paper's goal is to tackle this second issue, reducing the number of refinement steps without sacrificing quality. New thing from the paper, early answer convergence. The authors discovered that in many cases, diffusion language models internally figure out the correct final answer very early in the decoding process, long before it completes all its scheduled refinement steps. The model stop prediction for the answer tokens becomes correct and then stays correct for the rest of the decoding process. The remaining steps are essentially redundant, spent refining other parts of the text like the chain of thought or making tiny unnecessary adjustments. So the evidence, the authors ran experiments on benchmarks like GSM-8K, math problems, and general knowledge. They tracked when the model's internal prediction first matched the ground truth answer. On GSM-8K, using a technique called random remasking, 97% of correct answers had already emerged by the half point of the decoding process. And on MMLU, it's 99%. This discovery proves that there is a massive amount of wasted computation in standard DLM decoding. The model knows the answer, but it's forced to keep working. The solution: Prophet and early commit decoding. Based on the discovery of early answer convergence, the authors propose a new training-free decoding strategy. It's called Prophet. Prophet is not a new model, but an intelligent algorithm or paradigm for decoding. Its job is to monitor the model's confidence during the refinement process and decide the optimal moment to stop early. The core mechanism is called early commit decoding. So instead of running for a fixed number of steps, for example 50, this is the action of stopping the process early and generating all remaining mask tokens in one final shot. At each step, Prophet asks, is the model confident enough in its answer right now? If the answer is yes, it triggers the early commit, saving all the remaining steps. This is visualized perfectly in figure 3. Saving means like not redundantly doing all of the remaining steps. So how does Prophet decide when to stop? The crucial question: how does Prophet measure the model's confidence to make this early commit decision? It uses a simple but powerful metric. New thing from the paper: confidence gap. For any token position, the model outputs scores, logits, for every word in its vocabulary. The confidence gap is the difference between the score of the first highest ranked token and the second highest ranked token. So, for every position, you just check the highest probability token, its score, its confidence, and the second highest, and so the gap between those two. A large gap means the model is very certain about its top choice. Small gap means model is uncertain, as the second best option is a close competitor. Prophet calculates the average confidence gap across the tokens in the expected answer region. It then compares this average gap to a threshold. Dynamic threshold. Prophet is smart about this. The threshold isn't fixed. Early in decoding, the threshold is set very high. Prophet is risk averse and will only stop if the model is extremely confident. Later in decoding, the threshold gets lower. Prophet becomes more risk tolerant because the potential time savings are smaller and the model's predictions are more stable. Triggering the commit: if the average confidence gap is more or equal to threshold, the Prophet stops the iterative process and performs the early commit decoding. So the Prophet makes a single decision to stop for entire remaining answer at once, not token by token. The setup: the model starts with a sequence full of mask tokens where the answer should be. The capital of friends is, and then 5 mask tokens. The refinement loop: in each step, the model makes predictions for all the masks. Step 1, prediction, let's say PARUS, and then in the step 2, it makes here I, so this is more confident, and here it would be uncertain, here it would be more confident in the step 2. In the step 2, it's Paris. Prophets check the global confidence assessment. After each step, Prophet doesn't look at the confidence for just the first mask. It calculates the average confidence gap across all the tokens in the answer region, so all 5 tokens, the average confidence gap. Is the model on average very sure that P is better than any other letter in the first spot, A for second, R for third, and so on? The early commit trigger: when this average confidence is high enough, confidence gap is higher than threshold, Prophet makes the call. The final action: Prophet tells the model stop refining. Take your current best prediction for every remaining mass token and finalize them all right now. The loop terminates and the final answer is generated in one shot. So check out other videos on my channel and join my Discord, and that's gonna be it for this time.
Hello guys, quick update on my project Blueberry LLM from my Open Superintelligence lab, where we do all of this on Discord, by the way, not here, here. So I added this massive GPU support. So this project by NVIDIA Megatron LM, this is used to train like billion trillion parameter models on thousands of GPUs. So I added that to our LLM here. The goal of our LLM is for anybody to be able to download this and to just train on their GPU setup. So this LLM will automatically detect what GPUs, how many, what kind of GPUs, architecture, and then just automatically have the best possible training. So any company, anybody can train this. So it's like spreading the power of AI, democratizing AI. And I spent a lot of time doing that today. I have a lot of commits. You can see here issues. If you come here or on Discord, you can see like some research projects. So for example, for the parallelism, this is engineering project. I implemented this one, Megatron LM. Picotron is just for learning. It's smaller. I think it's slower as well. And then you can check these projects. You can come up with new research. You can write your research paper. You can practice engineering. And you can contribute here. So check the code, download this. I think if you just like run these commands, it should automatically train. What I have in plan next, I'm not sure. I need to like do more research, optimize, do more engineering. So you can contribute, just fork the repository, create a branch, and then create a pull request from your fork back to this. We need to also test like if this is all working. I was testing this Megatron LM a lot, but there is a lot more to test as well. But I think it works now. You can choose between. Actually, I just recommend using the native, the without. So don't use this. Use Megatron. Don't use this. This is just maybe for a lot of GPUs and it's still not so well tested. So just use this part or this. And I think that's gonna be it for this video. Contribute to this LLM. We're gonna make everybody be able to train LLMs. I wanna make it so good that OpenAI and xAI or Anthropic just use our code to train their LLMs. That's how good I want this to be. And there is a lot more of us and we can do it. So that's gonna be it for this video, and check out other videos or join Discord, and see you in the next one. See you tomorrow.
Let's check this paper, Decoder Hybrid Decoder Architecture for Efficient Reasoning with Long Generation. This paper introduces a new neural network architecture called Sambai, designed to be highly efficient, particularly for tasks that require generating long sequences of text, such as complex reasoning. The core innovation is a simple yet effective component called the gated memory unit, which allows different layers of the model to share information efficiently. By integrating GMUs into an existing efficient architecture, Yoko, the authors create Sambai, their largest model, 5-4 mini flash reasoning, and this is by Microsoft, by the way, so they use their own 5-4. I mean this paper demonstrates a superior performance on difficult reasoning benchmarks compared to a strong baseline 5-4 mini reasoning. Most importantly, it achieves this while being significantly faster, delivering up to 10 times higher throughput when generating long responses. The problem that they are solving is the cost of long generation. So you know that when LLMs are reasoning, they create a lot of tokens, and Transformer struggles. It has quadratic growth with the sequence length, number of tokens. And then linear models like state-space models and RNNs, they have linear scaling, but they omit a lot of information, lose a lot of information as the sequence grows. Hybrid architectures like Yoko improve efficiency by using a self-decoder with efficient layers like SSMs and one full attention layer. I actually have this kind of model that on my channel, it's called I trained my first LLM that speaks coherently, something like that. The KV cache for this single attention layer is then reused by all subsequent cross-attention layers in a cross-decoder. This makes processing the initial prompt fast, linear time. However, during the generation phase, every new token still requires all the cross-attention layers to read from the large KV cache, creating a memory input-output bottleneck. So every new token requires all of the cross-attention layers to read from the large KV cache, which creates a memory input-output bottleneck. The paper aims to solve this generation stage bottleneck, making reasoning with long chain of thoughts much more efficient. Core innovation: the gated memory unit, GMU. It's a mechanism for efficient memory sharing between layers. A GMU at a given layer L takes two inputs, the current hidden state X and the memory state M from previous layer L. It then uses the current state X to gate or control how the information from the memory M is used. How it works: the operation is a simple element-wise multiplication. Output is memory at, this is maybe element-wise multiplication, gate that passing in input through the gate, and then multiply with weights, which is the learnable matrix. The intuition: this allows the model to dynamically and selectively reuse representations from earlier layers. The current layer's input acts as a query that recalibrates the token mixing that happened in a previous layer, but in a much cheaper way than a full cross-attention operation. A bit tough to understand. The proposed architecture Sambai. Sambai is a novel decoder hybrid decoder architecture that applies the GMU to the Yoko framework. The architecture consists of self-decoder. This part processes the initial prompt. It uses Samba, an architecture that interleaves efficient Mamba (SSM) layers with sliding window attention. It contains only one full self-attention layer. So here we have Mamba, sliding window attention, Mamba, full attention. Then memory caching. After the prompt is processed, two things are cached: the KV cache from the single full attention layer, as in Yoko, the output state from the final Mamba SSM layer. This is a small constant size memory piece. Cross decoder. This part generates the response token by token. Instead of using only cross-attention layers like Yoko, Sambai replaces half of the expensive cross-attention layers with cheap GMU layers. The remaining cross-attention layers read from the large KV cache. The new GMU layers read from the small constant size SSM output state. So here you see after full attention we have this GMU cross-attention, GMU cross-attention. This design leads to significant efficiency gains. Prefill efficiency, like Yoko. Processing the initial prompt has linear time complexity. Generation efficiency. During the coding, the memory input-output cost is drastically reduced because half the layers perform a constant time GMU operation instead of a linear time cross-attention operation. This leads to a massive speedup for long sequences. Half of the layers perform a constant time GMU operations instead of linear time cross-attention operation. Okay. Key experiments and results. The authors conducted extensive experiments to validate Sambai's effectiveness. Scaling behavior. To ensure fair comparisons, the researchers developed a principled method called MuP or microprocessor ++ for scaling hyperparameters. These experiments show that Sambai scales better than other architectures. It exhibited a lower irreducible loss, which suggests that as more computational resources are invested, Sambai's performance potential is higher than that of the baseline. It's very good on benchmarks that involve context retrieval, long context retrieval. Interestingly, here we have differential attention. This was the big thing, like the big paper, but this is the first time I'm actually seeing it in use. So benchmarks are good. I wouldn't trust benchmarks so much. Only time will tell. Time is the best benchmark. Conclusion: the paper successfully introduces the Gated Memory Unit (GMU) as a powerful tool for efficient inner layer representation sharing. By creating the Sambai Architecture, the authors present a model that excels at both performance and efficiency, particularly for reasoning tasks require a long generation. That will be it for this video. Thank you for watching. Check out other videos on my channel and see you next time. Hello guys, I will show you how I set up my AI research. So how I write code locally on my computer with all of the AI ID, AI help, and then execute that code on a cloud, a GPU, how to connect it, how to run it very quickly, or Google Colab, and how to do everything smoothly. First method, which I don't recommend, but it's easy. You go to Google Colab, you select here change runtime type, and you select T4 GPU, and then whatever you code, you copy this code, Control A, Control C, you go back to your environment, you paste it here. So this is cursor, I talk with cursor, I talk with AI, I tell it what changes to make, and then after it's changed, I copy this code back, and then I just paste it here with Control A, Control V to replace everything, and then run. So this is one way. You can also paste this code directly into ChatGPT or Claude, but then it would rewrite the entire code. And this one is very long, so it could make mistakes or change things. So I recommend using like IDE here, where you can track what's happening and approve or reject changes. The second method is a lot better. I will show you how to run it on both free Google Colab GPU or a cheap but a lot better cloud GPU, whichever you choose. So this step is always same. So you go to your GitHub repositories and you create a new repository. You give it repository name, you maybe generate readme, you can select here Python for git ignore, and I recommend MIT license for fully open source, and then you say create repository. You can ask ChatGPT what any of these means if you don't know what they mean, or what GitHub is and how to use it, and etc. After you create a repository, I want you to clone it onto your local host. I will show you how, and on Google Colab. So we will make changes and edit in our local host, and then we will push changes to GitHub, and then pull them to Google Colab, run them on Google Colab, and that's how we will use it with local editing and then running on Google Colab. Or we will run it on a cloud GPU. It works same. So let's copy a URL to our repository, and you can ask ChatGPT how to clone it, but I will show you one way I do this. So in cursor or any IDE, I'm gonna go here, click file. I know you don't see it, but I'm just clicking file and new window, and then clone repository here. If you don't have this, then you need to do a different way, like using a terminal, ask ChatGPT. But if you have this, you can paste your URL here and then click here, and after you click this, it will prompt you, it will open a window for you to select where to clone it. So after you select that, you can press, it will ask you to open that cloned repository in a new window. So just click yes, open, and it will open like this. So I have it here. So I will edit my code here. I will talk to cursor. Whatever I do it here. Let's say I just make like some changes, just some comments here, okay? Then I save it. And you can again ask ChatGPT how to push changes, how to commit and push changes to GitHub. But I'll show you, we can go here and then leave a message, like comment, whatever. You will maybe read this later, but I don't spend a lot of effort. You see here, I just say fix. This is because I'm not working with other people, but when I start working with other people who might have to use this, or if I'm gonna have to use this, then I'm gonna put more effort into this. But it was just quick, trying quick, so I didn't put a lot of effort into comments. So I press commit, and then sync means like push. Or you can just go here and then push. Now on our GitHub, if we refresh this page, Here we have our comment. I know I misspelled it. I see that I misspelled it, but we can also enter this file that we just changed. No, I didn't misspell it. Anyways, this is our change that I added these two characters here. Now, let's copy this base URL. Okay, so not this blob, but just base URL. And let's go to Google Colab. I'm gonna create a new code cell and !git clone, and then paste the URL without anything after this. This is the name, the last thing. And then let's run. Make sure to connect to also like GPU if you want to use GPU. Then a new code cell. I need to put a %cd and then this name, because this is now the folder in which we need to enter. So if we go here you see this is our new folder, so we need to enter this. So now we entered it in our workspace, and if I want to run this LLM py file, which I want to run, so first I entered, so now we entered in that workspace, so now we can access this LLM py. So I say Python LLM py and then just run. And this should immediately start the training. It should run this file. Now, if I need to, so it's training here. If I need to make some changes here, let's say I make another change, I save. I go here, write some comment, commit push. So now it's on GitHub. Now I need to pull that change to this Google Colab. So I'm gonna stop this. I'm gonna make a new cell, !git pull, and that's it. And you can run with Shift Enter. And you see now we have this new change. So it's very quick, it's very fast. And this is the best way that I know of. You make some changes, you quickly push, you instantly pull, and that's it. I think it's very quick. If you want to push from Google Colab to GitHub, I don't do that, but I will show you later in the video after I show you this other method, and it's gonna be same. And the best way to do this that I'm actually using is I'm just spending 18 cents per hour, 18 cents per hour for a lot better, faster GPU than Google Colabs. I'm using Novita AI, they have the cheapest, 18 cents per hour, so I can click here GPUs or instances and create a new GPU instance. I will immediately change on demand to spot billing. And I'm gonna change template, and because this spot billing is 50% off, and in my experience they will not interrupt you, because it's like you can get this 50% off, but we will use the GPU when we need it. But we will give you 1 hour in advance notice. But in my experience, they never interrupted me, so this just works. And here, change template. I'm gonna use this one. Just search for this one and use that. I will just click deploy, and I don't need to change anything, just next, and make sure it's spot, and then deploy. So we will wait maybe a few seconds. Once you have it running, so you need to wait a little bit. I'm gonna go here, connect, and you can connect to this command. But first, we need to configure the public key. So copy this, you can click to copy, and then replace, so put your email here that you used to create the Novita account. To start a new console or terminal, you can go here. I know you don't see, but there is a terminal button here, or there is here on top here, you see this is the terminal. Or you can just search for terminal or console, or ask ChatGPT. Then go to your console. I'm just gonna start a new console and paste that here. I'm gonna just press enter to take defaults. I'm gonna overwrite. So we have this file, IDED25519. I think you should get the exact same name. If you don't worry. I'm gonna just press enter. I don't want any phrase or anything, passphrase. So I just pressed enter to everything. And then I need to see my public key. So I will copy this part of the output. I need to show it maybe this name to ChatGPT. Or you can just copy this below. These commands are all in the description. So I think this one for my Mac. So I'm gonna say cat and this. You can write this manually or copy from description or copy from ChatGPT. I will paste it and run it in terminal. And now I will copy this entire, so this is our key. So all of this entire thing, including the beginning, SSH, and the email. And then I need to click here settings to add this public SSH key. And just, this was my old one, so I'm gonna replace this old one and say update public key. And that's it. But you do this only once, and now you don't need to do this again. If your GPUs don't show, just click this refresh button here. So now every time you create a new instance, you just go here, connect, and copy this. And that's it. And then if you run it here, this is how it's so easy, it's so simple. You don't need to set up your key every time. And now I just say yes and press enter, and it's gonna connect now. There is, oh wait, is there password? Maybe only the first time you connect, you need this password here, just copy. But I didn't experience passwords, like it didn't ask me before. Maybe just the first time you connect with your key, and maybe never again. So I just pressed Ctrl V. It didn't show anything because it's not gonna show password in the console. I just pressed Ctrl V to paste and enter, or you can maybe click paste here as well. Now let's copy this again, the GitHub thing, and I'm gonna say git clone, and like this, copy, paste it, and then just press enter. And now it's cloned immediately, so I'm gonna cd and start typing the name of our repository name, so AN, and press tab. It will autocomplete because this is the only name. And now I'm in this, so I can just Python llm.py to run this, but I can just say like this, but it will say there is no data sets. So I'm gonna quickly show you you don't need to do this. I'm gonna say data sets and transformers. So we need these two things. So I made some changes in my localhost. Now I'm gonna push this to GitHub, and I'm gonna say git pull. So this is how we pull changes from a local host. Okay, now we pulled that requirements txt file. So this, I use this because it's very simple and fast. In this case, I will pip install -r requirements.txt. You will usually need this every time you start a new instance in new GPU, but it's fast because when you delete the GPU will terminate the instance, then it will like remove your everything you cloned or installed, so you need to do this again. You can also connect entire IDE onto the SSH server, but I experienced Cursor and these AIs being very slow there, so that's why I code on localhost and then I just push. But if you want to try connecting entire IDE, then you need to go here into extensions and look for remote SSH. I already have it installed, so it's this one. Make sure it's this one. So this one. Then you have two ways of using it. So you can open this menu here and say Remote Explorer, or you can also press Ctrl-Shift-P and start saying Remote SSH Connect to Host, and then configure SSH host, and for me it's this one, but so you can use either of these methods. But wait, I don't know if you can configure it on the sidebar, so you need to use this method to open this file to configure it, and if you get stuck at any point, you need to just ask ChatGPT. By the way, I don't do any of this, I don't connect it, but you can, but this is just if you want to try. And then you see, you need to basically put this command into this kind of format, which is actually very easy. I will leave you, you can copy this whole thing exactly the same, because we have this URL here, it's same as this URL without root. So this URL, we just need to copy this, change this port. It's every instance has its own different port, and now everything else stays the same. we created this file. So now I can maybe refresh this and then connect. And now this will connect. Okay, it doesn't connect for some reason. The reason it doesn't connect is this was different. So I need to copy this part here after the root at, and I will paste it here. Host name, I'm gonna paste it here, and then I'm gonna connect. And now there is no error, it starts to download. Let's copy this password again, and I will paste it here, press enter. And that's it. It's going to ask you for the password, by the way. If it doesn't ask you, then you don't need to do it. Okay, and then we can open folder, but after this starts downloading, you can click open folder, you'll see you are connected, and then you can choose your folder that you cloned. But I will interrupt this because I don't need this. So that's all I do. Now I'm gonna show you how to contribute from this remote to GitHub, which I don't do, but maybe it's very rarely. To connect it to GitHub so you can push from SSH to GitHub, you should find this github.com/settings/keys. You can just type this as well or click the description below. Then you need to run the same key generation command on your remote cloud GPU. So go into the terminal where you connected to the cloud GPU. Here I'm on cloud GPU, and I'm gonna run the same command. You can find it below the description. I'm just gonna press enter. Everything same command as generating. Okay, and then show this key as well. I will just copy it. Once you copy it, here in GitHub settings keys, create a new key. Whatever the name is, just for you, it doesn't matter. And paste your key and click add SSH key. Then go back to your cloud GPU and run this command, ssh-t git@github.com. I'm gonna leave it below as well. And now you successfully authenticated. So now we have the key on the GPU, which we connected to the GitHub. And before we had key on our local computer, which we connected to the GPU. Then you need to set the user who's gonna be pushing stuff onto GitHub. So just copy this command below. Also, we have git config username and then your name. I think it doesn't matter. Maybe it does. I'm not sure. Maybe it has to be same as GitHub name, or maybe it doesn't. I'm not sure. And then git config user email, and maybe I think this has to be same as GitHub account email that you are pushing from. So paste these two commands and that's it. So that's it. Now, because we cloned this repository from GitHub and we seeded into it, now we have GitHub repository initialized, everything is initialized, everything works. From this point on, you can do the classic git init, git add, git push, but you don't need to initialize here because it's already in a repository. I think we don't even need to set like the URL, but here I'm gonna run this command. So git remote set URL origin, and then git@github.com. So I'm gonna put my repository here. I'm gonna leave this command below, but I think you don't need to run this because this will already be automatically set because you just cloned the same like repository, so it will push to the same repository you cloned. But I'm gonna leave some commands below for you to help yourself, and you can copy them to ChatGPT to ask what they do. And any error you can also copy to ChatGPT. This is also how you can push stuff from Google Colab to GitHub. I'm gonna create a quick txt file here just to see like if this works. So I'm gonna git add dot to add all of the new changes, git commit changes txt file, whatever. I'm gonna send a message and then git push. So make sure, I think it will automatically work. You don't need to like set the remote URL because it will work because you already cloned it. Let's see if it works here. It looks like it's pushing. It looks like it worked. So now in my local host, I'm gonna go to my GitHub and here 3 dots and pull. Okay, so that's it. We have new examples txt. So that's it. It works. Now GitHub. Now we can push from remote to our local and to GitHub. That's it, guys. Once you generate key for Novita for your SSH GPU, you just click here connect, copy this and run this in your terminal, and that's it every time. You don't need to generate key. But if you want to connect GPU to GitHub, you need to generate key every time and connect it, because it gets deleted every time because it's on GPU and it all gets deleted. Okay, and once you finish, you can say stop to pause or to terminate. I'm going to terminate now. We got another open source version of DeepMind Genie that lets you walk and interact with the world, walk through the world. It's called the Hunyuan World Voyager, and today we will learn how Tencent made it. This framework can take a single image and transform it into a consistent and explorable 3D world. So a single image. This innovation addresses significant challenges in the automated creation of immersive digital environments for applications like gaming, virtual reality, and film. This tutorial will break down the complex concepts behind Voyager into an easy to understand step-by-step guide. There are multiple problems with creating a 3D world from a 2D image. Long-range spatial inconsistency. As you move further away from the initial viewpoint, the generated world can lose its structure and coherence. Visual hallucinations. AI can invent details that don't make sense or are inconsistent with the rest of the scene, especially in areas that were hidden in the original image. Complex 3D reconstruction. Turning the generated views into a usable 3D model often requires a separate, time-consuming process that can introduce errors. And World Voyager is designed to solve all three of these problems to an extent. This is one step in the research, and this technology is getting better and better with every paper. Voyager is using a video diffusion model. So Voyager actually doesn't just generate the RGB colors of the scene, it also generates a depth map. This is what a depth map looks like. You see, these lighter points are closer to the camera. So by generating both colors and the depth map, it gets this 3D effect. And the 3D structure, and everything is always in sync. To create a new view along the camera path, Voyager first takes the initial image and its estimated depth map to build a preliminary 3D point cloud. So this is what a point cloud is, and it seems like all of these different research areas are coming together now. This point cloud is then used to project a partial view from the new camera angle. This partial view, which includes both color and depth information, serves as a strong guide for the AI, preventing it from hallucinating inconsistent details. So this is example. We have this input view, and as we are moving the camera around, you see here it's just showing if we don't use depth map, it has some of these visual artifacts. It's a bit inaccurate, while RGB and the depth map here on top of RGB on top of that map, it's better. It doesn't have so many artifacts like this one here. To ensure the generated video frames strictly follow the geometric conditions, Voyager uses specialized control blocks within its structure. These lightweight modules reinforce the influence of depth and color guidance through the generation process. Generating a short video clip is one thing, but creating a world you can endlessly explore requires a more sophisticated approach. This is where Voyager's long-range exploration techniques come into play. World caching with point culling. As Voyager generates new video frames, it continuously updates a world cache of 3D point cloud. By the way, culling means killing a lot of things quickly, so maybe removing a lot of these points quickly. This cache acts as the memory of the entire world that has been seen so far. To keep this memory efficient, a clever point culling method is used. It intelligently removes redundant 3D points while preserving the essential geometric information, preventing the cache from becoming too large and slow to process. This is a cool way to have memory, but only the most important points to remove the less important information. Autoregressive and smooth video sampling. To generate long videos, Voyager uses an autoregressive process, meaning it generates the video in overlapping segments, with each new segment building upon the previous one. To ensure a seamless transition between these clips, so it generates multiple overlapping clips, a smooth video sampling technique is applied. This involves averaging the overlapping regions and performing a few extra denoising steps to iron out any visual discrepancies. So when they are merging multiple clips, they have these overlapping regions, and so they merge them on top of them, and they can also denoise a little bit there as well. Again, denoising there to make the transition look good. To train an AI model as powerful as Voyager, a massive amount of high-quality data is needed. This data must consist of videos with precise camera pose and accurate depth information. Since such data is scarce, the Tencent team developed a scalable video data engine to create it. Looks like we're gonna have this data with camera movement, 3D world movement. Now many companies create it and publish it, because it seems like all of these companies are creating their own data. So this is gonna be popular, so now we're gonna have open source data for that as well, probably, I'm guessing. Join my Discord, by the way, link below, and tell me if that link works. Some people say it does, some people say it doesn't, so I'm not sure. This engine can take arbitrary videos and automatically estimate the camera's movement and position for each frame, calculate a geometrically consistent depth map for the entire video, ensure that the depth scale is consistent across different videos, allowing the model to learn from a diverse dataset. Okay, this is a bit confusing. Depth scale is consistent, but anyways, they are not using video game engines like Unity or Unreal to create these videos. Looks like they are creating them with different AI models, this data, by just estimating depth from actual videos. Using this pipeline, the team curated a dataset of over 100,000 video clips to train Voyager. Now, is 100,000 even a lot? I'm not sure if it's too much. I don't know if it's a lot or not. There is more technical detail in how this is made. They have a lot more details. So I'm not sure if I'm gonna read this, if we're gonna re-implement this or something like this, or next version, some of the other papers like this. For now, that's gonna be it for this video. Those who want to research this are gonna go deeper into details here, and see you next time. Hello guys, new paper by Sakana AI. It's about using multiple different models or neural networks to combine them to create one that knows all of these things that different neural networks know. And this is so crazy. You don't need to actually pre-train or build new model. You can just combine different models, and it's so crazy. They took some random neural networks with random numbers, completely useless, not trying to do anything. And they used their method to pick the best parts of those neural networks and created a new neural network, new Frankenstein, new combined, that can actually do a simple task of classification of MNIST digits of these images. So from random useless numbers, using their method, to actual neural network, although simple one, that actually works without training it. So this is a lot easier, faster, simpler to do with than training the neural network to do the same task. And in other experiments, they combined LLM that knows math and one that knows agentic tool usage, and got a new LLM that knows both and can solve tasks, that math tasks that require agentic tools, a lot better than either of these two. And they have more experiments. The way they do this is they take two models, so they're gonna merge 2 by 2. So first they merge two models, and then they take this model and another model, and then they merge like that. So they merge 2 by 2, but you can merge as many times as you want. So we start from a bunch of different models, and we start from some tasks, some data. For example, you want to solve mathematics using tools or calculators. So you're gonna test all of these models that you have in the beginning to find which ones are good at maths, which ones are best at tool usage. And so you find the best at maths, and then this is the trick. So you don't actually find the best at tool usage. You find the best model that's complementing this math model. So best model that has something what this model cannot do. So in this case, it will be tool usage randomly. But the point here is we have a task. We find the best model for that task, And then we find other best model that's gonna complement what this model still cannot do to solve this task. So then we merge those two models, and now the new model will know both tasks. And let's say we have now this model and we test it on data and it still maybe struggles a bit. So we find another model that's now gonna complement this new model, and we merge those two, and now it's even better on the data. So, and you'll see later the technique of merging the models. So this is important. They don't actually decide which parts are gonna, like how are we gonna merge which parts of the models. For example, we will just merge these layers or these attention heads. No, model decides itself how it's gonna split and which parts it's gonna merge. This is also a new innovation. So the whole model, the whole neural network will be just one long string or array of numbers. And then their technique will decide where to split that into two and then merge these halves, these two halves, the first two halves of the two models, and merge the second two halves of the two models by averaging the weights. But we don't just average those weights. We also have some multiply, like for example 20% of this and 80% of this, and then sum, and 60-40 and then sum. So now let's go step by step. If this is confusing, don't worry. We're gonna repeat it or explain it in one or two different ways, so you will understand everything eventually, and you will be able to even read this paper if you want to for more details. This paper introduces a new and powerful method for merging machine learning models called Model Merging of Natural Niches, or M2N2. Traditional model merging combines pre-trained models by mixing their parameters, for example weights, according to predefined fixed groups, for example entire layers. This paper argues that this approach is too restrictive and inefficient. M2N2 proposes a more flexible and effective approach inspired by natural evolution. It features three key innovations. Flexible merging boundaries. Instead of merging fixed layers, it can split and merge models at any point, allowing for much more granular and effective combinations. Competition for niches or niches. It encourages a diverse population of models by making them compete for data points. A model gets more fitness if it correctly handles a data point that other models struggle with, naturally preserving a wide range of specialized skills. Attraction-based mating. When choosing two models to merge, the parents, it intelligently pairs models that have complementary strengths. It picks a second parent that is good at the things the first parent is bad at. The authors show that M2N2 can, for the first time, evolve efficient models entirely from scratch using only merging. It also scales to large, complex models like LLMs and image generation models, achieving state-of-the-art results for demonstrating an impressive ability to combine skills without forgetting abilities it wasn't explicitly optimized for. So, adding new abilities by combining but not forgetting important abilities that are necessary, or not forgetting any other abilities. Let's see. The problem with existing model merging. Imagine you have two expert books, one on mathematics and one on literature. You want to create a single, superior book that combines their knowledge. Existing method, fixed boundaries. This is like only being allowed to swap entire chapters. You could take chapter 1 from the math book and chapter 1 from the literature book and average them. This is very rigid and might not create a coherent result. So the way I understand this is they average weights of two different methods, but new averaged weights may not necessarily make sense. I mean average weights of two different models, not methods. Also here you are manually deciding that chapters are the right unit for merging, or for example layers in a transformer or layers in neural network. The limitation. This manual grouping of parameters into layers, attention blocks, etc. severely limits the possible combinations you can explore. The best way to combine the models might involve mixing paragraphs, sentences, or even individual words, not just entire chapters. The M2N2 solution, a nature-inspired approach. M2N2 is an evolutionary algorithm that maintains a population or archive of models and iteratively improves them through merging. Here is how its three core ideas work. Number 1. Evolving the merging boundaries. Flexible split points. Instead of merging fixed layers, M2N2 works with the model's parameters as one long continuous vector. When merging two parent models, A and B, it picks a random split point anywhere along the parameter vector. Merges the parameters before the split point with one mixing ratio and the parameters after the split point with a different ratio. The way I understand it is you have some numbers, some weights in one model and some weights, some numbers in the other model. And so this ratio mixing is you take, for example, 20%. So you multiply these numbers here with 20%, 0.2, and these numbers with 0.8, and then add them up. So that's how you mix those two parameters. And then it says here they have a random split point. So you split those. So you have one ratio for one part, 20/80, another ratio for the other part, 60/40, for example. Effect. Over many generations, a new model is created from a mosaic of tiny pieces of many different ancestors. This allows the algorithm to explore a much larger and more fine-grained search space of potential model combinations. True. Finding solutions that fixed boundary methods would miss. Number 2. Managing diversity via competition. Natural niches. Model merging works best when combining models with diverse, complementary skills. If all their models are good at the same thing, merging them doesn't add much value. M2N2 ensures diversity with a clever mechanism inspired by ecology. So we have data points as resources. Think of each training data point as a source of food or fitness. Limited resources. The total amount of fitness available from any single data point is limited. Competition. If many models in the population can already solve a particular data point correctly, the fitness reward for solving it again is reduced for everyone. The result, a model is rewarded more for being good at tasks that the rest of the population is bad at. Okay? So the more models can solve the task, the less reward they get. But if just one model can solve the task, then it will get a big reward. So now it's rewarded to solve what and nobody else can. This incentivizes models to specialize in different niches. One model becomes an expert on classifying cats, another on dogs. This maintains a population of diverse specialists, which are perfect ingredients for powerful merges. This is more elegant than manually defining diversity metrics. For example, preserve a model that's good at odd numbers and one that's good at even numbers. So instead of defining this manually by like humans deciding, there is a search. We just search for things that one model is good at and others are not. Attraction-based pairing. In nature, mate selection isn't random. M2N2 applies a similar principle to choosing which two models to merge. Select parent A. The first parent is chosen based on its overall fitness, how good it is. The second parent isn't chosen based on its own fitness, but on its attraction to parent A. So B is attractive to A if it performs well on the data points where A performs poorly, so they complement each other. Effect. This process explicitly pairs models that cover each other's weaknesses. It's an intelligent heuristic that makes the merging crossover operation much more likely to produce a superior offspring model. So they did these experiments evolving MNIST classifier from scratch. Task. Create a neural network to classify handwritten digits. This is so funny. M2N2 was able to evolve a high-performing classifier starting from a population of completely random, useless networks. So they are not trained, as I understand, completely random numbers. This is first for model merging. It achieved performance comparable to a powerful standard evolutionary algorithm, but was much more computationally efficient. So then they tried creating LLMs by combining LLM specialized in math, like Wizard Math, and LLM specialized in agentic tasks, like Agent Evol. And then the merged model performed better on tasks that required both of these. So if you need to solve a math problem with agentic tool use, then this merged model performed better than either of these on that problem. The main advantage here is that you can create big models without a lot of compute, without pre-training, by just merging different good models. Then they created this image generation model. So they took a very good model that generating images very well, but it only speaks English. And then they took some other model that speaks Japanese, understands Japanese prompts, and then they took that part, or they merged it such that those parts that understand Japanese are now able to generate using this English model good generator. So the new model is gonna generate very good images using Japanese prompts. And it was not only state of the art on Japanese prompts, but also retained its ability to understand English prompts, even though it was never optimized for English during the M2N2 process. This is a big advantage over traditional fine-tuning that can suffer from catastrophic forgetting. This is when you teach it to do one thing, it changes the weights, so now the weights, they were encoding some other information before they were changed, so now they don't anymore encode that information anymore. That can happen, so that's catastrophic forgetting. But in M2N2, in this case, this doesn't happen, and it seems like the way I understand this, it's a lot less likely to happen, or it doesn't happen, or probably a lot less likely to happen. Join my Discord where we do research together, we learn together, we're gonna publish research papers. We already have some research projects going on. We wanna structure this the same way you would do PhD or masters or work at a company. This would just be an open source contribution, and you can master your skills of AI research engineering, and we also have like studying lessons and everything. Or I'm trying to build it all. This is still a new couple days old, so you can just come and see where this goes. But we wanna start publishing like good quality papers, a lot of them, even at the scale of a company or a lab. Check out other videos on my channel, and see you next time. A new paper for training reasoning models. Usually the problem is reinforcement learning reasoning models, they just check the final step. And so even if there are incorrect reasoning steps that lead to correct final step, they reward that whole reasoning process if the final step is correct. I mean the final answer to the question. If it's correct, all of the steps, even if they are incorrect, are rewarded. This method comes up with a new way to check each reasoning steps, not just the final answer. So we teach the LLM to have correct reasoning steps, and not just randomly luckily get to correct answer with wrong reasoning steps. First, we will train the LLM or tell the LLM to generate its reasoning steps in these chunk tags, because otherwise it's difficult to know what exactly are reasoning steps. So LLM will generate reasoning steps in these chunk tags, and then each chunk tag we will check separately, evaluate separately as a reasoning step. So for each of the chunk tags, we check, we generate the complete completion 16 times, for example. And then how many of those 16 completions, starting from the current chunk, lead to correct answer? The more of them lead to correct answer, the better this chunk is. But generating 16 completions for every single chunk in every single response is expensive. So we will actually train another judge model, and we will train it to judge the chunks without the completions. So we will train the judge model by just giving it the chunk and the score for that chunk, and the score for that chunk is calculated based on how many completions of the 16 are correct. But the judge model will now learn to evaluate a chunk with a score without needing to generate 16 completions. We just generated the training data to train the judge. So now, judge will be just able to look at the chunk and assign a score, if it's good or bad. And by the way, so we will not assign like score from 1 to 16 or something. We will just have good or bad. And it will be, for example, based if more than 10 are good, like 10 answers are correct, 6 are incorrect, then that's a good chunk. Another method would be if more answers are correct than with the previous chunk. So remember, LLM is trying to reason using these chunks. And if it generates the next chunk, and now all of a sudden more of the 16 answers are correct, this means the chunk provide improvement compared to the previous chunk. So it figured something out new. So now the judge will learn to evaluate this chunk as good because it provides improvement. Now more answers are correct. For example, more of these 16 answers are now correct, so this is an improvement. So now let's explain this paper step by step, and I'm going to explain this all over again, but step by step. The big picture, the problem, and the solution. The problem: LLMs are now solving complex math and logic problems by generating a chain of thought, a series of intermediate reasoning steps. The challenge is ensuring these intermediate steps are logically correct. The traditional method of only checking the final answer, called outcome reward modeling, is inefficient. A single mistake early on can ruin the whole situation, but you only find out at the end. A better approach is process reward modeling, which evaluates each step of the reasoning. However, the paper points out two major flaws with existing PRMs. They are black box classifiers. They simply output a score or label correct, incorrect for a step without explaining why. They don't generalize well. They are typically trained with supervised fine-tuning on static, pre-labeled dataset, which limits their ability to adapt to new reasoning patterns. Also, the problem is that LLM is gonna start reward hacking, and it's not gonna solve the task, but create some hacks or avoid what we intended it to do, but just to get more reward. The stepwise solution. The authors propose a radical shift. Instead of treating the evaluation of a reasoning step as a simple classification task, they reframe it as a reasoning task itself. I really like this. Their model, Stepwise, is a generative judge. When asked to evaluate a reasoning step, it first generates its own chain of thought explaining its analysis. This is called meta-reasoning, reasoning about reasoning. Only after this analysis does it deliver a final verdict. Crucially, this judge is trained using reinforcement learning, allowing it to learn and improve in a more dynamic online fashion. There are three steps in Stepwise method. Chain of thought generation with self-segmentation, chunks of thought. The problem: what defines a step? Simply splitting the chain of thought at every double new line is a poor heuristic, so this is new paragraph. It often breaks up a single logical thought into multiple incomplete fragments. So when you want to reward or analyze a step of the LLM, what is a step? So how do you separate a single step? How do you see what a single step is? You cannot just do like a double new line because there could be an equation that's correlated to the sentence above, so that's still a single step. This makes it difficult for a judge to evaluate any single fragment in isolation, any single part of the LLM output. The solution: teach a policy model to segment its own reasoning into logically coherent units, which the paper calls chunks of thought. How it's done? They generate a set of correct chain of thought solutions from a base LLM. They use a more powerful LLM Llama 3.170b with a specific set of rules, see table 1, to segment these solutions by inserting chunk tags. The rules ensure each chunk has a unified purpose and represents a complete logical leap. They then fine-tune the original base model on this newly segmented data. Result: the policy model, which is the LLM that generates text, learns to automatically generate its reasoning in these well-defined, self-contained chunks. This provides a much better unit of analysis for the judge and replaces the total number of steps that need to be evaluated, saving computational cost. Stepwise data annotation, labeling the chunks. The goal, now that we have reasoning trajectories broken into meaningful chunks, we need to create training data for our judge. This means assigning a good or bad label to each chunk. The method, they use Monte Carlo rollouts to estimate the Q value, success probability before and after each chunk. So let's see, Monte Carlo rollouts, a simulation technique. To evaluate a step, you let the model generate many possible future paths, rollouts, from that point onwards. The quality of the step is then estimated by the average success rate of these rollouts. Average success rate of the rollouts estimates the quality of the current step that generated all of those rollouts. Q value, in this context, the Q value of reasoning step is the estimated probability of reaching correct final answer, starting from that step. It's calculated using Monte Carlo rollouts. So Q value is assigned to a step and it's calculated by checking using Monte Carlo rollouts and seeing how good rollouts, how good future steps this step leads, and the probability of success of all of those future steps. For each chunk, they estimate the Q value before the chunk was created and with that chunk created, to see if that chunk is gonna increase the probability of correct answer in the end. Each Q value is estimated by generating M, for example, 16 full completions from that point and calculating the fraction that led to a correct final answer. The more led to a good final answer, correct final answer, the higher the Q value is. Based on these Q values, they assign a binary label, plus for good, minus for bad, using one of the three strategies. Absolute Q value, the simplest method. If the Q value after the chunk is greater than 0, the chunk is labeled good. If it's 0, it's bad. Relative effective reward, rel effective. This strategy rewards progress. It considers not just the final Q value, but also the increase in the Q value from before to after the chunk. So how much did it increase the Q value? A step that raises the success chance from 10 to 50% is rewarded. A relative ratio, rel ratio, a simpler relative method. A chunk is good if the ratio of the Q value after to the Q value before is above a certain threshold. For example, 0.8. The paper finds that relative signals, rel effective and rel ratio, produce better judges because they incentivize forward progress rather than just avoiding terminal failure. Step 3. Training the judge via reinforcement learning. The goal: train the stepwise judge using the label data from step 2. The method: instead of simple supervised fine-tuning, they use online reinforcement learning. Task formulation: the judge is given the problem, the reasoning history, and the current chunk to evaluate. It is prompted to first generate an analysis, its own chain of thought about the chunk, and then a final judgment, boxed positive or boxed negative. Reinforcement learning reward: the training signal is simple. The judge gets a reward of +1 if the final judgment matches the label derived from the Monte Carlo rollouts in step 2 and 0 otherwise. So they use Monte Carlo as the real judgment, and then they are training a judge to just reason about if this step is correct. And judge needs to learn how Monte Carlo would evaluate it. Optimization algorithm: they use GRPO, and a reinforcement learning algorithm designed for training generative models. The judge generates multiple judgments, receives rewards, and updates its internal parameters to produce better analysis and more accurate judgment in the future. Prompt dataset balancing: they observe that good chunks are far more common than bad ones. To prevent the judge from simply leveraging to always predict positive, they balance the training data by downsampling the majority class. This was found to be critical for stable training and good performance. Okay, so most of the chunks are positive, are good. So I guess they want to actually make more bad chunks in the training dataset, so the judge doesn't always just say positive, good, this chunk is good. So they evaluate stepwise on these benchmarks and it performs well. They also use the judge to curate better fine-tuning data. How it works: generate multiple solutions for each problem. Instead of picking the one with the correct final answer, use stepwise to score every chunk in every solution. The solution with the highest average chunk score is selected. Result: fine-tuning a model on this high-quality judge-selected data produces a stronger final model compared to other selection methods. That's it for this video. Check out other videos on my channel and join my Discord where we do AI research.
OpenAI just released a new paper, Why Language Models Hallucinate. Hallucination is when a language model produces plausibly sounding but incorrect statements, text, sentences. And OpenAI says it's not weird, it's actually expected due to the way language models are trained and especially evaluated. The main reason for hallucinations is that LLMs are trained to guess, not acknowledge truth, but guess, and there is no penalty for wrong guess. So they are just guessing the next word, the next token. In this case, LLM is encouraged to always guess even if it doesn't know, because it can randomly get the correct answer, the correct word, but it will not be punished if the word is wrong. Also, our benchmarks are actually rewarding models that guess and accidentally give the correct answer, and not rewarding models that admit they don't know the answer. So all of these benchmarks we see, it's better for the LLM to always guess, and it will get a higher benchmark score because it's sometimes gonna guess the correct answer, as opposed to LLM telling it doesn't know. Then it will get lower score. It will never guess accidentally the correct answer. So we need to change that, and it makes a lot of sense. So the way I understand this is wrong answer should give negative points. Correct answer is positive, and saying it doesn't know, it should just remain 0. No point, negative or positive. That's how we want to train the LLM to behave. Firstly, the paper argues that even if you had perfectly correct training data, because the way LLMs generate text, they are still guessing and predicting, so there will still be wrong answers. Also, they also say that it's easier to check if the statement is correct or not than to generate a correct statement. So here we have a correct statement. There are 2 D's in ladder, which is correct, and incorrect statement, there are 3 L's in spell. So it's easier to train a model to judge which statement is correct than train a model to generate a correct statement. What this tells me is we should not try to create LLM that never hallucinates. Instead, we should have a separate model, maybe LLM, and then use this first LLM to generate a lot of statements, and use this separate LLM to find is this statement true or not. So generate a lot and then pick true ones, correct ones, as opposed to trying to make it only generate true statements. They also have a formula for that, which is crazy. They say that it's 2 times more difficult not to generate hallucinations than to judge them, to know which one is hallucination, which one is true. And this was a simple task, simple experiment where they figured this out, that they did. Let's go back to reasons why model simply doesn't know the answer. Maybe there is not enough information in training data, or the information doesn't exist, or model's architecture is not good enough, not powerful enough, or not suited for the specific task. For example, models are not good at counting letters because they operate on tokens, on groups of letters, so they don't see letters, they see groups of letters. And some problems are just too difficult, like breaking encryption. So here, the best thing it can do is guess, which will almost certainly lead to a hallucination. And they analyzed MMLU Pro GPQA SWE and Humanity's Last Exam, the scarily named benchmark. And all of them are giving 0 for models saying I don't know. And so models are rewarded for providing a best guess if they don't know. So hallucinations a lot of the time. We need to change this. This is important. We need to change this like quickly. So when these benchmarks need to punish wrong answers, give 0 for I don't know, and give points for correct answers. And I mean give negative points for wrong answer. And even these hallucination benchmarks that we have are not enough. We should change these main benchmarks to punish hallucinations.
Hello guys, so I got some plan for my new startup Open Superintelligence Lab. My problem was we want to do open research, but there is infinite amount of things we could be doing, so I don't know what we should do. Then I realized we want to try to be as useful as possible. So AI and superintelligence will be intelligent in the way we build it to be intelligent. So I think it will be super intelligent in mathematics code maybe, and it will be less than human level in some other things that humans are good at. That's not so necessary. We don't need AI for that. And when people say general superintelligence, that's actually very difficult to define because human intelligence is not so general either, it's narrow. So we can measure our goal, our progress, our research in terms of usefulness. And since we're not gonna sell anything, we're not gonna be able to get a lot of money. So we can just do research. So my idea is we will try to solve everything that we can do with just computers. So for anybody who has a lot of compute, 200,000 GPUs, they should be able to just download our code and run, and it should train the model on 200,000 GPUs. So that's the idea. So for that, we don't need money. We just need to do like research and engineering. And that allows anybody in the world to contribute without having to sell a product to make money in some way. So we can purely contribute to research and engineering and science that's gonna benefit, it's gonna have big benefits long term, without any short-term sales of anything. So to summarize, since we're not gonna get 200,000 GPUs of compute, I think we're not, maybe somebody will borrow or give us or something, but what we wanna do is create plug and play LLMs, video models, JEPA, whatever. And so companies or countries, governments, whoever has the GPUs, they can just download. And maybe one guy, one developer, or not even machine learning engineer, just a regular developer, can just run our code and it will train like a state-of-the-art model on 10 trillion tokens or whatever. This will spread the impact of AI to everybody. It will not just be a few companies that have all of the talent, all of the money. It will be, and recently, if you know, Qwen just released a new model. It's a hybrid attention and linear Mamba style model. So it was single-handedly invented by, I think, one person, Songlin Yang, and I don't know how much her two co-authors helped her. But this is an example of where one person or three people changed the course of AI field. So she's PhD student at MIT, and they just used their gated delta net. And I don't know if NVIDIA also used her work. I think also NVIDIA used her work as well. So this is an example of like one person or three people changing like everything. So Open Superintelligence Lab is a way for anybody in the world to contribute to AI. You can learn, you can become very good, you can create inventions that everybody starts to use. And I want us to be the best, better than XAI, OpenAI. I want them to just take our code and train the model. That's how much better we are, because there is a lot more of us. So I made 4 repositories here on GitHub Open Superintelligence Lab, and here Blueberry LLM. So this is a finished large language model that I coded, and it's very simple to train it. It can train on even small, you can run on Google Colab, free GPU, but you need a bit more compute to actually make it speak coherently. You can just run this with Python. It will automatically download dataset. It will do everything. So this is hyper optimized. I optimized this as much as I could. So any of you who know, like, who can help me here, you can create suggestions. I have some research ideas, so we can try this paper here to see if it's gonna train better. We also have some like ideas here, but I'm still thinking how I wanna structure this. So maybe we wanna like make this should be a lot bigger, and it can automatically detect how many GPUs there are, and maybe automatically tune hyperparameters to have the best training, so that anybody can just download and run, and it automatically uses all of the GPUs and trains as good of a model as possible. So recently Elon Musk has been saying like, we're not gonna use word AI researcher in XAI, it's just engineer. And actually I completely see where he's coming from, because engineering is what's actually useful, and it all comes down to engineering. So research is maybe same as engineering, except you put your findings in a paper, you think a bit more like how to communicate it and how to help others replicate it. But at the end of the day, we all need to be like top tier engineers. So give me suggestions on how I can structure this, so you already understand the idea. It should automatically do everything, detect GPUs and everything. And then I also have 3 more repositories, but they're empty right now. So for Blueberry video, video diffusion model, text to video, image to video, I'm thinking of maybe using this dataset, open with 1 million. I didn't yet code it. I'm gonna be coding it, so you can also help me with this. So again, somebody can just download this, let it run. It's gonna train like very good text to video model, image to video model, and maybe we can have like multiple versions, multiple types of training. I think what we're doing here is really good. I think a lot of people will want to donate or give us compute, borrow, maybe NVIDIA, maybe Hugging Face, maybe other. I already have Novita AI giving us some compute, and we can collaborate with them. Maybe even Alibaba Quen. I know they collaborated with some outside researchers on some of their models. But anyways, we just want to make AI accessible to anybody. And we want to solve the problem of having talent. So yes, they still need compute, but it's a lot easier. Money is a lot easier to get than talent. So scientists, researchers, a lot harder to get than money and compute. So buying GPUs is a lot easier than getting top AI talent. Here for Vision language model, there is one 4th-year PhD student who just joined our Discord, link below. So check the link below for Open Superintelligence Lab Discord. And he does like visual language models. So I'm gonna ask him what we should do here. So check this out, and you can come here, contribute, fork, make pull requests, or talk to us on Discord. And quite surprisingly, OpenSuperintelligenceLab.com was available, so I just bought that domain. It was available for some reason. But guys, I need your help, I need your ideas. I explained like my idea. We wanna make so good open source models and infrastructure and code that XAI, OpenAI, they just download our code as opposed to like doing their own, because there is more of us, we work harder and we're gonna make it better. And they're gonna focus on, I don't know what, maybe they're gonna contribute to us as well after we crush them. No, sorry, I'm kidding, I'm joking, sorry. And I do believe if we work hard, companies and people will give us compute. They're gonna give us a lot of compute, and we will be able to train and open source publish our models. But it only depends on our skill and hard work. Join the Discord link below. We have really good smart people here as well. And see you in the next video, which is maybe tomorrow. They made a new AI agent system that generates posters, so converts your or any research paper into a poster. So this is what it looks like. If we take some research paper, you see this is what it looks like. It puts in images, text. I can zoom in even more, so you can see the poster generated here. And you can see this poster as well. So it has 3 columns. It puts these images, calculates text size, how to put text and everything. I'll show you some more. So you see here, just this one on the right side. You see this one and this one. And now we will go step by step and understand how we generate colors, how the agent works itself. So we have different agents, layout agent, curator, designing, director. We have a layout which it is using. You can find the code here. And in the GitHub, you see how to run the code and use it yourself. Now let's go step by step and understand how these agents work if you want to code, understand, or research this yourself, or improve this one. The core problem. Researchers often need to create posters for academic conferences. This is time-consuming and difficult task because it requires not only summarizing complex research, but also applying design skills to make the poster visually appealing and easy to read. Existing tools often fail in one of the key areas, aesthetics and design. They might pull the right content, but the final poster looks cluttered, ugly, has overlapping elements, and requires a lot of manual fixing before it's usable. The proposed solution, Poster Gen. The authors propose a new system called Poster Gen. The key idea is to create an automated system that thinks and works like a team of professional designers. Instead of using one single massive AI model to do everything, Poster Gen uses a multi-agent framework. This means it has several specialized AI agents, each with a specific job that collaborate to build the poster. This approach is aesthetics aware, meaning the principles of good design are built directly into each agent's logic. The foundation core design principles. Before building the agents, the authors identify 4 core principles of effective poster design, which Poster Gen is built to follow. Narrative. A good poster tells a story. Poster Gen uses the and, but, therefore, ABT structure. And here's the established context or background, but here's the problem or gap in knowledge. Therefore, here's our solution and what we found. Layout structure. To ensure a natural reading flow, Poster Gen uses a strict 3-column grid. This layout avoids chaos and places the most important visual anchor at eye level in the center column. It also heavily utilizes white space to separate elements and reduce clutter. Color design. The system uses a limited and harmonious color palette. It extracts a theme color, often from the author's university logo, and generates a monochromatic scheme for it. A high contrast accent color is used sparingly to highlight key terms, ensuring readability. Typography design. Clear font sans serif are used to create a visual hierarchy. Different sizes are used for the title, headings, and body text. Semantic hierarchy is created using bold, italics, and the accent color to emphasize important words. The multi-agent workflow in action. A Poster Gen's process is divided into stages, with different agents handling each stage. This mirrors a real-life design workflow. Parser and curator agent, a content and storyboard. Parser agent, this is the first agent. It takes the research PDF as input. It extracts all the raw text and images. It distills the paper's core message into the ABT narrative structure. It organizes the text into logical sections and classifies all images by their function, key visual, main result, method, workflow. Curator agent, this is a creative director. It takes the structured content from the parser. It designs a storyboard, deciding which content goes into which of the 3 columns following the ABT narrative. It enforces a limit of 5 to 8 sections to prevent the poster from becoming too crowded. Layout agent, spatial arrangement. This agent takes conceptual storyboard from the curator and makes it concrete. Calculates precise coordinates, x, y, and dimensions with height for every single text box and image on the poster canvas. A key technical challenge it solves is accurately estimating the height of the text box, which is difficult in the programming library used, Python PPTX. It uses a clever binary search algorithm 1 in the paper, to find the perfect height without the text shrinking or overflowing. It uses a CSS-like box model to precisely control the white space, margins and padding around every element, ensuring a clean, balanced look. And then styling agents applying aesthetics. Color agent. This agent creates and applies the color scheme. It analyzes the author's affiliation logo to find a primary theme color, then generates a harmonious palette based on it. Font agent. This agent handles all the typography. It uses an LLM to identify important keywords in the text. Then it applies different styles, font size, bolding, italics, accent colors to create a clear visual and semantic hierarchy. Renderer. Final production. This final module takes all the metadata, content, coordinates, sizes, color fonts from the previous agent. It uses the Python PPTX library to programmatically generate a final PPTX file. Finally, it converts this file into a high-resolution PNG image ready for the user. To evaluate these generated posters, the authors created a detailed scoring rubric, stable one, that assesses both content fidelity and design quality. Instead of relying only on human judges, they use powerful vision language model as an expert judge. They gave the VLM the rubric and the generated posters and asked it to score them. And if you combine a GPT-4o image generator to their poster agent is better if you just give entire paper to either of these.
Hello guys, quick video. New Qwen 3 Next is absolutely crazy. 80 billion parameters, almost beats 235 billion, the biggest one. And you see here it's beating this one benchmark, this benchmark, and it's approaching. So overall it's almost as good as the biggest one. It's 10 times faster than the previous, a lot smaller model with 32 billion parameters. And it can generate multiple tokens at once natively, which is crazy. And it has just 3 billion parameters. And it seems like we are surpassing transformer, we are surpassing attention mechanism, we are getting new linear architectures. So here, gated delta net, let's see the architecture here and how they are achieving these insane results with such a small model. I'll quickly go over this because it's just an update. I'm gonna be making more videos about this. So linear attention is good and fast, but weak at recall, at remembering context. I think especially distant context. And standard quadratic attention is expensive and slow during inference. Through systematic experimentation, which is what we are actually gonna do, I'm gonna be trying this myself as well. They find that gated delta net is actually better than sliding window attention and Mamba 2. These are linear attention strategies. They found in their experiments that when they have a mix of gated delta net with standard attention with a 3:1 ratio, so 75% is gated delta net and 25% is standard attention, it consistently outperforms any model that only has standard attention or only has gated delta net in terms of both better performance and higher efficiency. They have some of these architectural tricks like doubling the head size and applying rope to only 25% of position dimensions. I'm not gonna go deep dive into this right now, I'm gonna do it in a different video. So only 3.7% of parameters is activated. This is crazy. Compared to Qwen's 3, 128 total experts. Qwen 3 Next has 512 total experts. And here we have 8 routed, so 8 active is what, only 8 routed, and I think it seems like there is no shared experts that always activate. So 8 are always chosen, there is no expert that always activate, and here we have 1 shared expert that always activates and 10 routed experts, so 11 in total. They found that if you have good global load balancing, meaning that tokens are an equal number of tokens is sent to each expert, then you can just keep adding experts and the loss will slowly go down. This is crazy. Why do we have convolutional layer here after linear? I have no idea. I'm interested in this. They have a lot of normalizations, so You see before mixture of experts, zero-centered RMS norm, and here, and they have RMS norm here within the gated mechanism. So you see this is gated delta net, and this is gated attention. This is why we have convolution. So I thought this was attention. Never mind, this was attention up here. But I still need to see what this is. And another crazy thing, they have multi-token prediction natively, so it actually predicts multiple tokens at once. Just like speculative decoding, but it's even better, it says here, because it's custom trained to predict multiple tokens in both training and inference, and it also performs it like training. Trains learns faster. Maybe we can do research paper on like a project here as well. So it's 7 times to 10 times faster than the 32B model. Look how the difference of the throughput scales exponentially, and this seems like the longer it is, the faster it is, or the throughput is higher. They also have installation guide, so that's gonna be it for this video, and you can just Google Qwen 3 next, and see you next time. Check out other videos on my channel, and see you next time.
This guy, Su Jianlin, who invented rotary positional embeddings, just wrote an article on MuP Optimizer. He works at Moonshot AI at Kimi K2, and let's learn from it. Let's say we have a 2D circle with radius w equals 1. So we are at any point at the circle, and at any point we denote as w. So that w is our weight from neural network. And we also get a gradient, which is an arrow showing us where to move that weight, in which direction in the coordinate system, to improve the loss of the neural network. The issue is that arrow most of the time will make the weight move off the circle. Very rarely there is a chance that it ends up on the circle again. To recap and to explain again, we have some number w, which is actually our weight in the neural network, but if you don't understand that, this is just a number. And we have some function, which is loss, the mistake of our neural network, but you don't even need to understand that. The only thing you need to understand is we need to find w, number that will give us the lowest value for this function. Here you see on this example, there is a very clear -7 if x, or in our case w, is 0, then our function, or in this case y, is -7. So at w, that is x 0, our function is lowest. So we need to find this number w. So how do we find, so we want to find our w for whatever function we have to be the lowest at that point of w. This is classic minimum of the function. Now what happens in neural networks is this w is actually a set of numbers, set of weights, so a matrix. Usually it's a matrix. And we pass this entire matrix through a function. And in practice, neural networks work well if length or strength of these matrices or vectors is 1 or very close to 1. So if this is confusing, it doesn't matter. All I want you to understand is that we need to find minimum of a function, but there is some constraint. And in this example, our weight is dot on a circle. So our weight has x and y components on the circle. And we want the distance from center to our x and y components to be 1, to be unit length. So you know the formula, it's Euclidean distance. It's x squared plus y squared and then the root of that sum. That needs to be 1. That's how you get all of the points on a unit circle. If you draw every point where x squared plus y squared and then root of that sum is equal to 1, you're gonna get the unit circle, all the points on the unit circle around one distance of one around center. If all of that is confusing, just remember that we need to find minimum, but the length of vector w must be 1, so it must be on the circle. We can just move it along the circle. And just to clarify, this function L, this is not the circle I'm talking about. This is a separate, unrelated function. And we need to find w where this function L has minimum value, but w has a constraint that it must be of unit length, of length 1. So w is a vector with x and y coordinates in this case. Now we are understanding how MuP Optimizer works, MuP Best Optimizer. So we take our gradient, which is another arrow or vector showing us how to change w to minimize that loss function that I was explaining. But since we only want to move on the circle, we will decompose that arrow to one arrow that's perpendicular. If this is circle, one arrow is perpendicular to the circle, and one arrow is kind of tangential or parallel to the circle. So if you move a bit in this direction, then you will stay on the circle. Not too much, because you will still go off circle, but if you move a bit, you will stay on the circle. So that's that parallel or tangential arrow part of the vector. And we discard the perpendicular component. We don't need that. This is the optimization problem, the formula that we have. Here we have our gradient that we will update weights with. As I said, these gradients will move our weights in any random direction. But we want to keep weights on some circle or sphere or some other dimensional object constrained. Our task is to find this phi that we will use instead of the gradients. So it should be as similar as possible to the gradients, that will minimize the loss, but when it multiplies weights, the weights will remain and should remain on this unit circle, sphere, or spectral norm, so the constraint. In other words, we need to find a matrix phi that is as similar as possible to the gradients, but follows our constraint. For this trace operation to work, to find the most similar phi to gradient, we must keep the magnitude of phi at 1. And we will see now why. This will not work otherwise. Let's look at some AI research, engineering, and projects, and let's see what we even want to learn. This segment anything has 50,000 stars. This means it's very influential research. Very useful. You get an image. Do you get also, I know you can do it in video in the latest one. You can just segment these objects. But this makes me think this is like solving a specific problem. But is this going towards general AI, like agent or scientist that can research AI, or some kind of general AI that's gonna help itself improve and become smarter? So I guess we have these type of specific problems and then this general AGI kind of issues. So Meta has X-formers and flex attention. So this is for building entire transformers quickly, and this is for just attention mechanism. It has fast kernels, optimizations, both of them. So X-formers is for training large models reliably, and flex attention for prototyping new attention mechanisms, also for research, I think. Then this Dino V3 is an interesting project. Training AI to understand video without any labeling data. So here it understands where the road is, where the bike is, it understands depth, it understands many different things about the video. This could be at the path to general intelligence. It can be used for classification, segmentation, detection, tracking, retrieval, depth, so many things. It's interesting and good, but I need to investigate or inspect what things I want to learn and focus on, what I think is the best like for the future.
experienced Kimi researcher and inventor of rope, just wrote an article on why they chose MuP Optimizer. We discovered a rather astonishing conclusion. Under our experimental conditions, MuP achieves nearly twice the training efficiency compared to Adam. Research on optimizers is neither scarce nor overwhelming in quantity. Why did we choose MuP as our new direction to explore? How did we quickly transition from a well-tuned Adam optimizer to MuP? Regarding optimizers, I've previously offered a brief assessment. Most optimizer improvements are essentially minor patches, not without value, but they ultimately fail to deliver a profound or impressive impact. We need to approach a question of what makes a good optimizer from more fundamental principles. This is what I like. This is so interesting. Intuitively, an ideal optimizer should possess two characteristics: stability and speed. Stability and speed. Specifically, each update step of an ideal optimizer should, number one, minimize disturbance to the model, and number two, maximize contribution to loss reduction. More directly, we don't want to drastically alter the model stability while still significantly reducing the loss speed. The classic wanting to have it both ways. How do we translate these characteristics into mathematical language? Stability can be understood as a constraint on the update magnitude, while speed can be interpreted as finding the update that reduces the loss function most rapidly. This transforms into a constrained optimization problem, yes. Specifically for a matrix parameter W with dimensions n times m with gradient g, same dimensions, same shape. When the parameter changes from W to W plus delta W, so to next update iteration of parameters, the change in the loss function is...
I'm writing AI research paper. I have this large language model that I trained in some of my videos. It's always the same. So now I want to try to find different architectures. There is this repository, Flash Linear Attention. And this is just a repository of different students from different universities like MIT just creating their own versions of attention mechanism. Actually, most of them are similar. They're just a little bit different. It looks like they found something, because if most of them are similar, just a bit different, then it means like this is the good direction that they found. Just trying to figure out the best path forward. I will use some of these. They're already implemented in this repository, so I don't need to actually be able to code them from my memory from scratch. That's not what we do in research. I'm just going to understand how they work, the mathematics behind them, but not like entire history of mathematics and how it got derived. Just how the math works in the paper. And then I'm going to do research by just testing, trying different scales, trying different versions, drawing plots, measuring against my own standard attention mechanism language model. So one trap you could fall into if you are beginning with research is you think you need to understand everything from scratch, the whole history of everything. No. You just need to understand like how the math in the paper and how this works. And then don't spend time understand anything that you don't need. Instead, spend time doing the research. So we will understand all of the code, like how it works. We don't need to understand, this is the code base. We don't need to be able to code it from scratch, but just understand everything, how it works. And I'm using AI to code, but don't get lazy. You need to follow what AI is doing. Like you need to know what it's doing, what's happening here. At least on a high level, what this file does and what some of the functions inside. You see, we have some implementations, RetNet attention and stuff. So here we have controlled comparisons. Same training setup, only attention mechanism changes. All configs saved, deterministic seeding. I want to show you what happens. For example, I'm coding this with AI, but AI doesn't know what exactly files there are in some of these modules. So you can talk to it, tell it, okay, give me the command to run to check which files there are and which classes you can import. So you need to just keep the track of what's happening, and then I'm running the commands because I'm running this on the remote. So AI doesn't have access to this. So I'm running the commands, I'm giving it the pasted classes that it can import from this flash attention linear, and now it's fixing it. And now I think, okay, so we have a different error, but this is good, this is progress. And one important thing, so it couldn't figure out how to implement and use this code from flash linear attention, so I cloned it here. And I told it, you have it cloned now, you can read it now, and then it fixed all of the bugs, but it couldn't fix without it at all. Guys, I made autonomous AI experiment here, which is crazy. So 100% done by AI. Check one of my latest videos. But here, let's say we have a mixture of experts, and for some tokens, router is not sure to which expert to route it to. So it sometimes give it this expert, sometimes that expert, which is not good, because we want like router to be decisive to only classify some tokens to some experts so they can just learn those tokens or that kind of information. So we punish router for having like being indecisive. So I mean, AI came up with this experiment. So AI designed everything, the different LLMs working together. And so it came up with the idea to, if like two experts have very close probability, then there will be a bit of loss added to their loss. So AI LLM will learn not to assign similar probabilities. And it looks like the experiment worked. It improved perplexity 1.7, 5.7%. The experiment worked. I'm using Gemini, Kimi, I'm using from Novita AI Inference, GPU from Novita AI, and Inference Kimi K2 from Novita AI. It's very cheap. This is the whole plan that was derived from this AI. Starting from here, it was like 4-step plan. I mean, like there was 4 of these files. So first plan, then critique, then revise critique, and then final plan. And then I just pasted this into Grok code fast. I really like this idea. It involves a lot of reading manually these programs, but I feel like it can work. So the next idea would be to somehow create an agent that can start multiple researches. So right now we just starts one. The prompts and everything just start one. But maybe get some agent and start multiple, and then give it a goal to improve my LLM maybe 2 times. And then just run a bunch of different researches at the same time. But I think the main cost there would be GPU. So GPU per hour, that would be the main problem. Maybe somehow we can use more AI, LLM generations, and less GPU, maybe, I don't know. I think that's it for this video, and see you next time. Check other videos on my channel. Hello guys, here are some AI research ideas for beginners that will have actual real-world impact and that you can put on your resume. So I'm making this project, a Blueberry LLM, that lets anybody, any person, company download this LLM onto their GPU cluster or one GPU, whatever number of GPUs, and automatically train the best possible large language model. It's fully open source, so I create research projects and ideas as you would get in a real company like OpenAI. For example, here, if you go to issues, you see here like different tasks. So this task, let's say, you can just fork entire repository and open it in some AI ID like cursor and copy this task and tell it to help you. Here I tried training our LLM on T4 GPU, which is Google Colab GPU, and it turns out that this mixed precision, which should be faster, actually wasn't faster for some reason. Maybe the LLM was too small. So this task is to find out when AMP is faster and when it can be used over FP32, so mixed precision, automatic mixed precision. So you will learn, I want you to draw some graphs. You can use, by the way, different GPUs, not necessarily just this one. But this one is free GPU if you want. So there is no hard requirements for this research. I kind of left it open-ended for you to maybe draw some images, do some learnings. It doesn't have to be completely exhaustive, comprehensive. It's too difficult to do. So just try something and put some images here. And then I'm going to give you feedback. Somebody else will give you feedback. And we can help you as well. So we will all work together. So draw whatever, do whatever you can, do some research and write your findings here. We will have multiple people working on it. I also have a new ebook, $9, that will teach you how to code LLM from scratch, step by step. In just 45 days, you will learn everything from not knowing Python, how to code LLM from scratch. Link below. There are other issues, for example, testing different activation functions. I have a guy working on this already, but you can also help. He draws some things, but this is like a big research task. So this guy alone cannot do it alone. So you can also help. You can do your own stuff. We're gonna put some images here soon. By the way, you can go here, labels, and click research, and also click if you want a good first issue for beginners. And it will give you a few here. For example, this research also. Do we want to have a few big experts or a lot small experts in our LLM? And this is a too broad question. So you would need to constrain this, like maybe just do it on like for Google Colab GPU and do whatever you can. Don't get overwhelmed. You don't need to like solve this entire thing alone. This is a question nobody has solution to yet, but you can do what you can. And update us frequently. As soon as you do something, even if your thoughts about setting up the experiment, comment it immediately here and tag me. And I will be posting a lot more of these beginner friendly and even some advanced research experiments or tasks or things that you would get in a real company, DeepMind, OpenAI, Anthropic, if you go to work there. And you can also contribute to open source. I want this to be like the best project ever. Anybody can train their own LLM just by downloading. You don't need like to pay engineers. Anybody can train their own LLM on any amount of GPUs automatically, best LLM. We want to be so good that even OpenAI, Google, and all of them take this code, our code, and maybe do a bit of adjustments, but this code should be so good. In the other news, I made it automatically. If it detects you have a Tesla T4 GPU, it's going to automatically choose the setup, the config. Now, the config, we need more research to find the absolute best config, absolute best setup. That's why we want to do this research. But now it's able to detect and then choose config for this specifically. And I also have for RTX 4090 also detection. I'm going to also add a lot more different kinds of GPUs, different numbers of GPUs as well. I also have this new folder, speedruns. So the idea here is that you take some GPU or setup like T4 and you take 5 minutes and you train as good of a model as possible in 5 minutes. So for example, lowest validation loss, or maybe even some benchmarks if the model is good enough. But I'm not sure how this would work yet, because submissions I need to divide into maybe GPU categories or number of GPU categories or something. You can maybe put your ideas. So here on my Discord server under active research, I'm gonna put these projects so you can just pick them up. These are real world projects that you would get at OpenAI. So starting tomorrow, I'm gonna add a lot more of these projects. And lastly, I want to keep doing this open source thing full time forever. I don't wanna get a job and do something else. So I made this tutorial, 45-page ebook. Learn to code and train LLM from scratch in 45 days. Every day you have a single task. It's $9. So this is the way I'll be able to continue doing YouTube and this open source project full time without getting a different job. So that's why I made this. Here you have table of contents of every day, what you need to learn. And when you click either of these, you're gonna get this tutorial. But I actually recommend copying this whole tutorial and then pasting it into ChatGPT or Gemini. I like Gemini. And then you just can chat to it and learn. So it can answer your specific questions. We can check a different one, for example, load balancing loss. So you can help me do this full time. Just copy this. So my LLM that you will be able to code and train from scratch. This is the LLM. It's open source on my. So this LLM is open source. What this guide will provide is a step-by-step guide on how to learn it and all of the prompts, so you can self-study it. You can find this LLM, it's open source already on my GitHub, on my YouTube. Just look for publish your own LLM video. I think that's it for this video. I want this to be the absolute best, most useful project ever. So I don't want to lock us between some VCs or investors who will not let us open source. They will want to extract money from people. We will be so useless and be 1,000st AI company and compete for the scraps. No, instead, I want everybody from NVIDIA, Hugging Face, Novita, GPU providers, whoever, or other companies, consumer companies, product companies, to train their own LLM from scratch automatically. Maybe even non-developers should be able to do it. And we can get developers, engineers from the entire world helping us on this research. This could be like Humanities United Research, or other people could fork. I don't want to claim too much credit here. So other people can fork this and build their own versions. I want this to start like an open source revolution, where we share science and not lock it behind like closed doors, keep it in secret. Hello guys, we will explore how Bytedance made this model computer use agent that can use computers, web browser, terminal, and solve tasks on computer. And it's competitive with OpenAI, Anthropic's models, etc. And this is really good because they show step by step everything, how they build it, what they did, and the problems, the solutions, unlike these other companies, OpenAI, Anthropic. Somebody told me that I should explain more stuff with my own words as opposed to reading from the screen. So I read that feedback in the middle of recording this video. So first part of the video, I'm going to be reading more. The second part, I'm going to be explaining with my own words. And hopefully future videos, I'm going to try to explain with my own words more and more. This paper starts by identifying the central goal, creating an autonomous agent that can intelligently operate computers using graphical user interface, just like a human does. Think of it as an AI that can see the screen, understand a goal. For example, book a flight to New York, and then move the mouse, click buttons, and type text to complete the task. However, building such an agent is extremely difficult. The authors identify 4 major challenges. Data scarcity. It's hard to get enough high-quality training data, unlike text or code, which exists in vast quantities online. Detailed recordings of someone reasoning through a computer task, thought, action, result, are rare and expensive to create. Unstable reinforcement learning. RL is a powerful technique for teaching agents through trial and error, but it's notoriously unstable for complex, multi-step tasks. Rewards are often delayed. You only know if you succeeded at the very end, making it hard for agent to figure out which of its many actions were good or bad. Limitations of GUI-only operation. Many real-world tasks can't be done just by clicking and typing. A developer might need to run commands in a terminal or manage files in the file system. A pure GUI agent is limited. Environment instability. Training an AI agent requires running millions of simulations in virtual machines or browser sandboxes. These environments can be fragile, slow, and prone to crashes, which is major engineering bottleneck for large-scale training. UI TARS 2 is a system designed to tackle all 4 of these challenges. The UI TARS 2 methodology. How does it work? This is the core of the paper, where they explain their solution. First, the paper defines what the agent is and how it behaves. Concept: native agent perspective. This means the agent is a single end-to-end model. It takes in visual input, screenshots, and text instructions and directly outputs actions. There are no separate hand-coded modules for perception, planning, etc. The entire process is learned from data. Concept: react paradigm. The agent operates in a loop, mimicking human problem solving. At each step, it forms a cycle of reasoning thought. It thinks about the current situation, what the goal is, and what to do next. Okay, I see the login page. I need to type the username in the username field. Action: it performs an action in the environment. Observation: it gets feedback from the environment. A new screenshot showing the result of the action. And then we have concept: hybrid action space, GUI plus SDK. This directly addresses the GUI-only limitation. The agent can perform two types of actions: GUI actions, click, type, scroll, and similar, and predefined SDK functions, a set of special tools that go beyond the GUI, such as running terminal commands or managing the file system. This makes the agent far more powerful. The environment where the agent lives. To address the environment instability challenge, they built a robust all-in-one testing platform. They have this all-in-one GUI sandbox that is unified environment that can provide many different things for the agent. It has a shared file system where agent can do things like download file from the browser, which is a GUI action. And then it can maybe use terminal to process that file, which is all in the same session. It also has cloud virtual machines to run entire operating systems like Windows, Ubuntu, at a very large scale for training, pre-training. And then a specialized sandbox for browsers that runs web browser very efficiently and quickly. And it has some options to speed up time simulation, something that's happening in the browser. To solve the data problem, they have this data flywheel. So instead of creating all data at once and then training on it, they actually let data self-improve. A flywheel is a heavy wheel that once spinning keeps its momentum. So here wheel is the cycle of data self-improvement. In the beginning, they start to train with the initial initial model, and then use the new model to solve tasks. And then tasks that are easily or quickly solved. This is high quality data for supervised fine-tuning, and lower quality data where models struggled. They are not thrown away, they are just used for continued pre-training, but they are not like high quality for supervised fine-tuning at the end. And so you retrain the model and generate data again, and so on. So it's like a self-improving in this case. This is really nice in comparison to text models, because text models cannot actually generate, text models don't have some environment against which to check if their text is good. Maybe for just mathematics or code. But here in this GUI, the model actually can check if it's solving the tasks properly on the computer, if the task is solved. So this can generate data self-recursively. Better model generates better data, and so on. And then for the highest quality data, they have a human helping it, but the human is not gonna check the correctness. Actually, the human is gonna tell the model and suggest what to do. If human sees model making a mistake, it can immediately stop it and suggest it to do something else. So human is helping the model while it's training. The reward design. There are two types of tasks. Verifiable tasks where you can check automatically if the result is correct, and these other tasks where you cannot check automatically. So for the other tasks, they use another LLM like GPT-4 or 4o or Quen or whatever the better LLM to judge the correctness of the task. Wait, it looks like they use GPT-4 also for these verifiable tasks. So LLM for the verifiable tasks. And for non-verifiable tasks, open-ended tasks, that don't have a single correct solution, for example, they create an outcome reward model. This is a model trained specifically to look at the trajectory and predict a success score. In this case, they use UiTars2 itself as the ORM, so the model that they are training. There is another issue as well. So traditionally, you have a batch of tasks. So you have multiple tasks, all independent tasks, and you wait for all of them to finish, and then to reward the model, to update the model. Well, if one task is very long, then all of the other tasks just need to, so the GPU needs to wait, the model needs to wait until the longest one finishes. So it's a wasted time, wasted compute resources. Their system is asynchronous. It uses a streaming approach where training updates can begin as soon as a minimum number of tasks are complete, while the longer tasks continue running in the background. They use proximal policy optimization by OpenAI, but they have some more tricks added to it to make it more stable and effective for long, complex tasks. And instead of training a single model from scratch to know everything, GUI, games, coding, they actually train specialist models, one just for GUI, for web, maybe for games, for coding. In the end, they just merge all of those models by averaging their weights. And I have a recent video on how to train LLMs without pre-training, so just by averaging weights, or how to do this model merging better. This works surprisingly well because models trained from the same starting point tend to learn in compatible ways. It's a cheap and efficient way to combine diverse skills without extensive joint training. So instead of needing to have a separate data set that combines, for example, coding and GUI, we just train separate GUI, separate coding, and then merge them, and now it's gonna be good at tasks that require both of them, both coding and GUI. Their model actually outperforms even OpenAI and Anthropic on some of the benchmarks. They also found out that if you give it more time to solve problems, it solves problems better. So this is inference time scaling. So which means the model learned how to solve problems, didn't just maybe memorize solutions, but it learned how to solve problems. They also trained, when they teach a specialist model, on like SDK using commands, and then they merge with the GUI model that just knows GUI. Actually, now the new model is even better at the GUI. So it applies what it learned from SDK to GUI, and now it performs generally better. Check out other videos on my channel. Also, people say that my titles aren't accurately representing 100% what the video shows, so I'll look to improve that. It's actually not so easy to do. To summarize entire video in a single title, it's a bit difficult, but maybe I'll use AI to help me or something. SGLang is a fast large language model serving framework, but I'm pretty sure they also use it in training, especially in XAI. So all of these companies are using it. You can just create your own function and put sglang.function decorator above, and then get your system prompt, user prompt, and use sglang.generate to generate the answer, the result. It's very simple. We got a bunch of different stuff, different attention mechanisms, speculative decoding, different quantizations, FP4, FP8, int4, etc. So this front-end language layer in Python sglang is your interface that you can use. There is a bunch of different files here. And then backend, when you use the interface, this is what gets the work done. So entry points, engine py, the main engine class that orchestrates the entire serving pipeline. So this is the path to the engine, and we can see this class. So tokenizer manager tokenizes the requests and sends them to the scheduler. Scheduler subprocess receives requests from the tokenizer manager, schedules batches, forwards them through the language model, and sends the output of the language model back to the detokenizer. So detokenizer manager is gonna detokenize the output tokens and send the result back to the tokenizer manager for the next generation, or it can also send text back to the user. This architecture enables high performance parallel processing across multiple sub-processes. So that could be this scheduler generating tokens, and detokenizer as well. Efficient batching, smart scheduling of requests for optimal GPU utilization. Memory management, where separate processes prevent memory conflicts. Scalability, SGLang can handle multiple concurrent requests efficiently. This is why they use it at XAI, for example, and I think in XAI they are just trying to quickly build up, so they're using all of the made tools already. They don't want to reinvent the wheel. That's why they are also importing entire electricity power station, I think, from across the seas. So we have key features are radix attention for efficient prefix caching. So when you send a message, when you are in a conversation, this upper part of the message is always repeated. Every time there is a new message, all of this thing gets sent again. So you can just cache that without needing to recompute this first part of the message all the time. That's what I think it is. continuous batching, dynamic batch formation for optimal throughput. So these are like tricks for memory, GPU memory. Multimodal support, images, video, text inputs, structured outputs, JSON schema validation, regex constraints, distributed inference support for tensor, pipeline, or expert parallelism when you split the model across multiple GPUs, for example. All of these quantizations. So FP4 is just for inference, I believe, but maybe they will soon be for training as well. So then we got this stream executor, which is kind of maybe one of the main things. So it's asynchronous execution. It uses producer-consumer pattern. Variables are synchronized using threading events. Each execution context maintains its own state. Intermediate representations IR system. The IR system in IRPy defines the abstract syntax tree for SGL programs. So we have constraint generation, the regex and JSON schema validation at the IR level. API speculative execution, pre-computation of API calls for performance. To use SGLang, you can create a new Python file and then import it like this. Then we want to set this localhost as the default backend that's going to generate our large language model text and stuff. Then we can define a generation function, which is sgl.function, single turn question that gets S, which is entire conversation as I'm understanding, and then the question. So we add the user question and then we generate the answer under this answer key. So in this S state, under the key answer, you have your answer. S represents the state of the generation process, which is built up incrementally. .run executes the sglang function and returns the final state that contains the generated output. Generating JSON output is almost the same. We just define this JSON schema, so like this, and tell it in the prompt to generate JSON format. And then later, if we take what's under the key JSON output that we defined here, the key, we can just load that into the JSON. We can also run processes in parallel. So if we have our function that takes in the question and we have array of questions, run the generations in parallel by providing a list of arguments. So we just call this function single turn question with run batch and then provide list of these questions. And we can print all of the answers because run batch will return a list of states. So for S in states, we print the answer. So to use this sglang, you would need to pip install it, and then you need to have it running with some model, for example, llama. And then this will give you the port, and you need to connect to that port, which what I was explaining with the base URL, so localhost and the port from your script to be able to use this language model to generate this. Interactive chatbots require maintaining a history of conversations. sglang handles this efficiently by building upon its state object. The key is to construct the full conversation history with the sglang function for each new turn. So besides the state, you can also pass in history to create this multi-turn chatbot. History is a list of dictionaries where each dictionary represents a turn with a role and content. It's a bit confusing, but here, turn in history, we got turn role to be user and turn content. So I guess history is just a single conversation. It's a turn is a dictionary. So for user, you assign the content of the turn to sgl.user, and for assistant, you assign content of the turn to the sgl assistant. So this is like just a history that you store in your memory. This is how you create an interactive loop. So you just keep appending the new user inputs and AI responses to this history, and then just keep calling it with this history argument. I'm not sure why it's passing in history here, but not the state, but as I understand, because we are running .run, this somehow manages to pass in state as well to this multi-turn chatbot. And if you just run this script, you're gonna get the interactive chatbot script. Forking the parallel generation, so sometimes you wanna generate multiple outputs from a single input, single prompt, single user message. Maybe you wanna generate some options to choose from. So we have sgl.fork. So to our multiple endings to our generation function, we can have number of forks, number of generations for a single input. So here with sgl.fork, and then pass in the number of forks as fork. So this creates number of forks independent generation branches from the current state. But crucially, the computation for processing this input, the shared story premise, is done only once. And then you fork multiple generations. Inside the loop, we work on each forked state, f, independently, generating text and storing it in a uniquely named variable. For example, ending 0, ending 1. This is where we define the variable sgl.gen and the name of the variable. Just like up here, above, we were using sgl.gen with response key. So we will just now put a variable now. We can also pass this stream equals true when we call this run on our function, and it will get automatically taken care of. And this is how we catch the partial states and print it to the user. Here we see inner workings of sglang for those who want to build their own systems or modify sglang, etc. So our state object is not a simple string, it's a state builder that keeps track of the sequence of operations. And then with this plus equals, when you add plus equals like sgl user hello message to the state, this is what happens. So it seems like sglang defined custom handling of this plus equals in its class. So it kind of just appends this operation to the array of operations. By the way, you can define these like custom handlings with these kind of classes. Each of these things has its own function in a class, and you can rewrite it and define custom handling. Okay, well, that's gonna be it for this video. I think I'm gonna end it. You can join our Discord server where we do AI research, and see you next time. Check out other videos on my channel, and see you next time. Hello guys, today we made progress in Open Superintelligence Lab. Currently our main focus is the large language model, and we want anybody to be able to download this and run on their GPU cluster. Is it 1 GPU or 1 million GPUs? It should automatically figure out the best configuration and train the best state-of-the-art model possible, even by a person who doesn't know how to program. So here, if you click on issues, you can see some research idea for you and good first issue. So these are good beginner research ideas. If you click here, you can see I described some ablations you can do and test which one is best. Okay, I didn't even see, we already have somebody commenting here. So you can just take the issue. You can also create your own research or idea. And as I said here, I don't recommend changing the dataset, although if you want to research dataset in particular, then do it. But if you want to research architecture, then just keep this dataset. And I recommended here to try different sizes and to compare different functions with different sizes and see how it works. But it's up to this guy now to plan his research. So you can do the same, and I will help and provide feedback, and you can use AI to help you. Goal with this is to just improve the performance a bit, and we will also learn. This can also be turned into a full research paper, by the way. This is a good topic for a research paper, and it's wide enough, and this research is actually useful. It's going to be useful. So it's going to be in the real project. That was my main issue before I had this goal. There is infinite amount of possible research, and I don't know what to do. So now everything that's useful to this project of democratizing, of allowing anybody to have access to create AI, And before I continue talking about the LLM, I just want to quickly show you that we have 3 more projects: VLM, Visual Language Model, Video Generation, and Image Generation. So for video generation, I just want to start from Open Sora. So I think Open Sora is a good project. It's open source. We don't need to start from scratch. This is what open source is for. It's a mistake to start from scratch. So we can start from this guy and then improve on top of this. And we can have also automatically configurable auto training on any GPU numbers for anybody. And for vision language model, I want to start from a Nano VLM by Hugging Face. For image generation, I don't know yet, but right now I'm just focusing on the LLM. And this was actually built from scratch by me. I just found it best way to build it from scratch in this case, but it's not necessary if there is a good project already, although I didn't find any good project, so I just built one. So if you want to write a paper yourself, or you just want to contribute to open source, or you want to hone your skills, you can check out these issues. You can create your own issue and then do some of them. You need to scope them, as I explained, like plan them. And if we write any research papers, if I write them, I'm going to put anybody who contributed onto the research paper, depending on how much either co-author or in the, like maybe some kind of acknowledgements or mentions if it's a very small contribution. And if it's a decent contribution, then co-author. Anyways, I want to have like good goals with this. We want to do this very fast, very quickly. We want, as I said, we want OpenAI, XAI, everybody to just take our code and train. We want it to be so good because there is a lot more of us. There is a lot of us. We can do this. So I feel like right now all of these companies are inventing the same thing, reinventing the wheel, keeping the science secret. Doesn't make any sense. So we will do this, and we will also get compute. I think a lot of companies will be like giving us compute. Nvidia, maybe Novita, these other GPU companies, Hugging Face. But it depends on our skill. And I think this is easy for beginners as well. If you are now the absolute beginner, then it's going to be a bit more difficult. Maybe you can create your own maybe ticket or idea here, these issues, and then do something very simple, trying to improve something very simple. You can vibe code, you can ask, but make sure your vibe coded code is good. So don't make it bloated. And if you do, I will give you feedback and tell you how to improve. Maybe I will also improve, we'll see. But I think you need to be careful there. By the way, if any of you wants to work on any of these other projects, I'm not still sure what to do with them right now. I'm just focusing on LLM, but you can join my Discord, link below, and you can maybe create issue and tag me or ping me or something. And by issue, I mean like it's just like a task or idea, not necessarily like a problem issue. So I think this is really important project because here your research will serve a real value in the real world. There is infinite possible things to research, maybe infinite possible ideas, but only a small part will actually be useful. And it's gonna be, that's why I came up with this idea. To just have this project so anybody can download and run on their GPUs. It should automatically train the best possible model LLM. So feel free to go here into issues, create a new issue. Now think, how are you gonna think of something useful, something good for our goal? And so just describe your task, your idea here. Anyways, by the time you check this video, there will be a lot more research projects here, tasks, so you can check them, find ones you want, and do the research. You can write your own paper. Maybe we will write paper together, and we'll see. Okay, guys, join the Discord below, and see you in the next video.